Space feels quiet, not just silent, but completely empty. When most people imagine space, they picture darkness, stars, and maybe a gentle floating feeling. It looks peaceful, almost calm, like drifting in a dream, with nothing around you. But that calm feeling hides something much more serious, because in space, there is no air at all, not just thin air, but none, and that changes everything. Here on Earth, air is always around you. You don't notice it, but it's pressing on your body all the time. It's like being at the bottom of a very light ocean made of invisible gas. You're used to it, so it feels normal. But what would happen if that pressure suddenly disappeared? Imagine opening a soda bottle. You hear that quick pest sound, and tiny bubbles rush out. That's pressure escaping. Now imagine something similar happening to the human body, but without any warning. So what actually happens in space? The first thing is simple, but serious. You can't breathe. There is no oxygen to inhale, no air to pull into your lungs. And without oxygen, your body starts to shut down very quickly. How quickly? Faster than most people expect. You would likely stay conscious for about 10 to 15 seconds. That's about the time it takes to walk across a small room, or count slowly from 1 to 10. After that, you would lose consciousness. And here's something many people misunderstand. A lot of movies show people holding their breath in space, trying to survive a bit longer. But that's actually dangerous. Why? Because if you hold your breath while the pressure drops, the air inside your lungs can expand, and that can damage them. So the safer reaction would actually be to exhale. It sounds strange, doesn't it? In a place where there's no air, the safest thing is to let your last breath out. Now, there's another effect that surprises people. What happens to the liquids in your body? You might imagine your blood boiling instantly, like water in a hot kettle, but that's not quite what happens. Your body still has some internal pressure, and your skin helps keep things together, so your blood doesn't start bubbling wildly inside your veins. But some liquids closer to the surface can begin to form bubbles. This is because of something called low-pressure boiling. Here on Earth, water boils at 100 degrees Celsius, the temperature of boiling water in a kettle. But if you go to a place with very low pressure, like high up in the mountains, water can boil at much lower temperatures. In space, where pressure is almost zero, liquids can start to boil even at body temperature. So parts of your body would begin to swell slightly, not explode, but expand. You might puff up a bit, like a balloon being gently inflated. If you've ever seen bread dough rise slowly, it's a bit like that. But happening to soft tissues, it sounds intense, but it's not as dramatic as movies make it seem. And here's another common myth. People often think that if you're exposed to space, you instantly explode. But that's not true. Your skin is stronger than that. It holds everything together. You wouldn't burst like a balloon. Instead, your body would slowly react to the sudden loss of pressure. So if you don't explode, and you don't freeze instantly, what is actually the biggest danger? It comes back to oxygen. Without oxygen, your brain simply can't function. Think of your brain like a device that always needs power. Oxygen is that power source. When it's gone, everything starts to fade. Vision dims, awareness slips, and then nothing, quietly. No noise, no dramatic moment, just a slow fade, like a light being turned down. This is why spacecraft and spacesuits are built so carefully. They're not just there to provide air. They are like small, controlled Earth environments, tiny bubbles of safety in a place that offers none. Inside a spacesuit, there is pressure, oxygen, and temperature control. It's like carrying a small piece of Earth with you wherever you go. Without it, space becomes extremely dangerous very quickly. And yet, there's something fascinating about this. Because the danger isn't loud, it doesn't chase you, it doesn't attack. It just exists, completely indifferent. You could float peacefully, surrounded by stars, with no sound at all, and still be in one of the most dangerous environments imaginable. So why does it feel so calm? Maybe because we associate quiet with safety. On Earth, silence often means rest, a quiet night, a calm room, a peaceful place. But in space, silence means something very different. It means there's nothing there to carry sound. No air, no wind, no movement, just emptiness. And that emptiness is what makes space so dangerous. It's not trying to harm you. It simply offers nothing to keep you alive. And that's the key idea. Space doesn't kill in the way we usually think. It doesn't strike or attack. It just removes everything you need to survive. Air, pressure, warmth, protection, all gone. And when those are gone, the human body has only seconds before it begins to shut down. It's a quiet kind of danger, one that doesn't feel urgent until it is. And maybe that's what makes it so fascinating, because something can look so calm, so beautiful, and still be completely unforgiving. If you were drifting there, surrounded by stars, everything might feel still and endless, but behind that stillness, your body would be fighting to hold on, even for just a few seconds. And that's all it takes, just a few seconds, in a place where there is nothing at all. As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. Space is cold. That's one of the first things people imagine. A place so cold that anything exposed to it would freeze instantly, like touching ice that never melts. Movies often show this happening in seconds, person drifting out into space, turning solid almost immediately. But is that really what would happen? Not exactly. In fact, the truth is a little surprising. Freezing in space is much slower than most people think. And to understand why, we have to think about how heat actually leaves the body. Here on Earth, you lose heat in a few simple ways. One is through the air around you. If it's cold outside, the air pulls heat away from your skin. That's why standing in a cold wind feels so much colder than being in a still room. Another way is through contact. If you sit on a cold metal chair, it quickly draws heat out of you. Metal feels colder than wood, even at the same temperature, because it pulls heat away faster. And then there's radiation. This one is quieter. It doesn't need air or contact. It's just heat slowly leaving your body as energy, like warmth drifting away from a cup of coffee left on a table. Now here's the important question. In space, which of these methods still works? There's no air. There's nothing to touch. So the only way your body can lose heat is through radiation. And radiation is slow, much slower than wind or contact. So even though space is extremely cold, your body wouldn't freeze instantly. It would actually take quite a long time. How long? Long enough that freezing would not be the main problem at first. Think of it like this. If you place a hot drink on a table in a quiet room, it doesn't instantly become cold. It slowly cools down over time. Now imagine that same drink floating in space, with no air to carry heat away. It would cool even more slowly. So if someone were exposed to space, they wouldn't suddenly turn into ice. Instead, they would remain warm for a while. Warm enough that freezing wouldn't even be the first thing happening. This is where a common misunderstanding comes in. People often mix up cold with fast freezing, but cold doesn't always mean quick. It depends on how heat is transferred, and in space, that process is very slow. So what would you actually feel? At first, probably not cold at all. In fact, You might still feel the warmth of your own body, but at the same time, something else, much more urgent, is happening. Remember the lack of oxygen we talked about earlier? That would take effect long before freezing becomes noticeable. So while your body is slowly losing heat, your brain is already running out of oxygen, which raises an interesting question. If freezing is slow, what about the parts of space that are in direct sunlight? Because space isn't always cold in the way we imagine. If you're in sunlight, without any atmosphere to block it, the heat can be intense. Surfaces exposed to direct sunlight can reach temperatures hotter than boiling water, hotter than a pot left on a stove that's over 100 degrees Celsius, or about as hot as freshly boiled water. But just a short distance away, in shadow, temperatures can drop to around minus 150 degrees Celsius, colder than the coldest place on Earth. That's like standing next to a fire while your other side is in deep winter. So which one would affect you? The answer depends on where you are. If you're in sunlight, you might actually start heating up. If you're in shadow, you would slowly cool down. But again, slowly. Because without air, heat doesn't move quickly. This creates a strange situation. In space, you can be surrounded by extreme temperatures, but not feel them immediately. It's like being in a room where one side is a burning oven and the other side is a freezer. But you're wrapped in a blanket that slows everything down. Your body becomes its own small system, holding on to heat for as long as it can. And this leads to another question. If freezing is slow, could someone survive longer because of that? It might seem that way, but unfortunately, no, because temperature isn't the main danger. It's still the lack of oxygen and pressure. Those act much faster. So even though freezing takes time, the body doesn't get the chance to experience it fully. The more immediate effects take over first. This is why space is so unusual. The dangers don't always match what we expect. You might think the cold is the biggest threat, but in reality, it's something invisible and silent. Air, or rather, the absence of it. And yet, the idea of freezing in space still captures the imagination. Maybe because we can relate to cold more easily. We've all felt cold before. Standing in rain, feeling a cold wind, touching ice. But we've never experienced a complete vacuum. That makes it harder to picture. So our minds go to what we understand. Freezing, ice, stillness. But space doesn't behave like Earth. It follows its own rules, and those rules can feel strange at first. Cold that doesn't freeze you quickly. Heat that can exist right next to deep cold. Silence that carries no warmth at all. It's a place where extremes exist, side by side, but not always in the ways we expect. And maybe that's part of what makes it so fascinating, because the more you learn about it, the more it challenges simple ideas. Things aren't always what they seem. What looks like instant danger may take time, and what seems harmless may act quickly. So if someone were to drift into space, they wouldn't become an ice statue in seconds. Instead, their body would slowly begin to cool, holding on to its heat for a while, like a fading warmth that lingers longer than expected. But before the cold can truly take hold, something else would already be happening. Something quieter, faster, and far more important. Because in space, it's not the cold that reaches you first. It's the emptiness, and that changes everything. There's a moment that often appears in movies. A small crack forms in a spacecraft window. A faint hiss begins, and then suddenly, everything is pulled outward in a violent rush. People, objects, air, all dragged toward the opening. It looks dramatic, fast, almost like an explosion in reverse. But how accurate is that? What really happens when pressure suddenly drops to near zero? This is what we call decompression, and when it happens quickly, it becomes something much more serious. Explosive decompression. To understand it, it helps to think about something simple. Have you ever opened a tightly sealed container? Maybe a jar that gives a small pop when the lid comes off, or a bag of chips that feels slightly inflated when you first open it. That's pressure. Air pushing outward from the inside, balanced by the air outside. Now imagine that balance suddenly disappears. Inside a spacecraft, the air pressure is carefully controlled. It's designed to feel like being on Earth, or close to it. You can breathe normally, move comfortably, and your body behaves the way it's used to. But outside the spacecraft, there is almost no pressure at all. So what happens if there's a sudden opening? The air inside rushes out, not gently, but quickly. It's like air trying to escape all at once, moving from a crowded space into a completely empty one. You can picture it like opening a balloon. If you let go of the opening, the air doesn't slowly drift out. It rushes out, making that familiar fluttering sound as the balloon shrinks. Now imagine something much larger than a balloon, a room, a spacecraft cabin. All that air moving at once. So the question is, would a person get pulled out immediately? It depends. If the opening is large and you are close to it, there could be a strong force pulling you toward it. But it's not like a powerful vacuum cleaner pulling everything from across the room. The effect is strongest near the opening. Farther away, it becomes weaker, so not everything gets instantly sucked out. But the air itself does leave very quickly, and that creates a serious problem. Because as the air leaves, the pressure drops, and your body feels that change right away. What does that feel like? Imagine being in an airplane during a rapid descent, when your ears pop. That's a small pressure change. Now imagine that happening much faster and much more extreme. The pressure inside your body and outside your body suddenly becomes very different. Air trapped in places like your lungs, sinuses, and even your digestive system begins to expand. Just like the air in a balloon expands when the pressure outside is reduced. So what should you do in that moment? This is where something important comes in. If you try to hold your breath, that expanding air has nowhere to go, and that can cause damage. So the safest response is actually to exhale. Let the air out. It sounds simple, but in a sudden situation, it's not always easy to react that way. Now, what about the rest of the body? Would it explode? Again, this is a common myth. The answer is no. Your skin is strong. It holds everything together. You wouldn't burst apart, but you would begin to swell slightly as gases inside your body expand. Think of it like a loaf of bread rising in the oven. It expands, but it stays together. Your body would behave in a similar way, stretching a bit, but not breaking. At the same time, something else is happening. The pressure around you is dropping to near zero, and that brings us back to oxygen. As the pressure drops, the oxygen available to your body becomes almost non-existent. Even if there's still some air in your lungs, it's not enough, because without pressure, oxygen doesn't move properly into your bloodstream. So your brain begins to lose oxygen very quickly. This is the same timeline as before. About 10 to 15 seconds of useful consciousness. That's not long. It's about the time it takes to walk from one side of a room to the other, or to take a few calm breaths. And during that time, things would start to feel different. Your vision might narrow, like looking through a tunnel. Sounds might feel distant. Your thoughts might slow down. And then, quietly, you would lose awareness. No loud moment, no dramatic signal, just a gradual fading. Now here's something interesting. Explosive decompression sounds violent, but in many cases, it happens faster than the body can fully react, which means there's very little time to feel anything beyond the initial change. So even though it looks chaotic from the outside, from a personal perspective, it may feel brief, quick, almost confusing. and then gone. This is why spacecraft are built with so many safety systems, layers of protection, strong materials, careful monitoring of pressure at all times, because even a small leak can become serious if it grows. And in space, there's no outside air to balance things out. Once air starts escaping, it keeps going until there's nothing left. And that leads to another question. Could you hear it? In the movies, decompression is loud, a roaring rush of air, but in reality, sound needs air to travel. Inside the spacecraft, you would hear something, the movement of air, the vibration of structures, but outside there would be complete silence. No sound at all, just motion. This creates a strange contrast. Inside, noise, rushing air, movement. Outside, complete silence, as if nothing is happening at all. And maybe that's one of the most unusual parts of space. Even the most dramatic events can happen without sound, without warning, without anything to carry that sense of urgency. Everything becomes visual, physical, immediate. So when we think about explosive decompression, it's easy to imagine something loud and violent. But the real danger is quieter than that. It's in the pressure, the invisible force we don't usually notice, the balance that keeps our bodies stable. Once that balance is gone, everything begins to change, not in a dramatic explosion, but in a rapid, silent shift. Air rushing away, pressure dropping, oxygen disappearing, and in just a few seconds, the body follows. Because in space, even something as simple as air is everything. When people imagine danger in space, they often think about the obvious things. No air, extreme temperatures, floating endlessly with nothing to hold on to. But there's another danger that you can't see at all. It doesn't make a sound, it doesn't have a shape, and it doesn't feel like anything at first. It's called radiation. And in space, it's everywhere. Here on Earth, we are protected from most of it. The planet has a thick atmosphere, like a soft blanket wrapped around it. This blanket absorbs and blocks a large portion of the radiation coming from space. On top of that, Earth has a magnetic field. You can think of it like an invisible shield, stretching far out into space, gently guiding harmful particles away from the surface. Together, the atmosphere and the magnetic field act like a double layer of protection. So most of the time, we don't even notice radiation at all. But what happens when you leave that protection behind? In space, there is no blanket, no shield, just open exposure. Radiation moves freely, traveling across vast distances without anything to stop it. So what exactly is it? At its simplest, radiation is energy moving through space. Sometimes it comes from the sun, sometimes from distant stars, and sometimes from events so powerful they happened millions or even billions of years ago. These particles travel incredibly fast, close to the speed of light. That's about 300,000 kilometers per second, fast enough to circle the Earth more than 7 times. It's hard to picture that kind of speed. Imagine blinking your eyes, and something has already traveled around the entire planet multiple times. That's how quickly these particles move. Now here's the question. If they're so small and so fast, why are they dangerous? The answer has to do with energy. Even though these particles are tiny, they carry a huge amount of energy because of their speed, and when they pass through the human body, they can interact with cells. Sometimes they pass through without causing much harm, but other times they can damage important parts of the cell, especially DNA. DNA is like the instruction manual for your body. It tells your cells how to grow, how to repair, and how to function. If that instruction manual gets damaged, problems can begin to form. But here's something important. Radiation doesn't feel like an injury. You don't feel it the way you feel heat or cold. There's no immediate signal telling you something is wrong. So how would someone even know they're being exposed? That's the tricky part. In the short term, you might not notice anything at all. Everything could feel normal, calm, quiet. But over time, the effects can build up. That's why astronauts have to be very careful. Even though they are protected inside spacecraft and spacesuits, they are still exposed to more radiation than people on Earth. It's like standing outside in the sun. A few minutes might not feel like much, but over hours and days, the exposure adds up. Now imagine that same idea, but with radiation coming from all directions, not just from above, from the sun, from deep space, from events happening far beyond our galaxy. This is what astronauts face. So how did they stay safe? Spacecraft are designed with shielding, layers of material that help reduce the amount of radiation that gets inside. It's not perfect, but it helps. And missions are carefully planned to limit exposure. Time becomes an important factor. The longer you stay in space, the more radiation you receive. So every mission has to balance exploration with safety. This leads to an interesting question. If radiation is everywhere in space, does that mean deep space is even more dangerous? The answer is yes. Low Earth orbit, where the International Space Station stays, is still partly protected by Earth's magnetic field. It's like being near the edge of a protective umbrella. But if you travel farther out, toward the moon, or beyond, that protection becomes weaker. Eventually, it disappears completely, and then you are fully exposed. It's like stepping out from under a roof into open rain. There's nothing left to shield you. This is one of the biggest challenges for long space journeys. Traveling to Mars, for example, would take months. During that time, astronauts would be exposed to continuous radiation, so scientists are always looking for better ways to protect them. Stronger materials, better shielding, new ideas that can reduce the risk, because unlike other dangers, radiation doesn't announce itself. It doesn't rush at you. It doesn't create a sudden moment. It's slow, quiet, constant, and that's what makes it so unusual. You could be floating peacefully, watching the stars, feeling completely safe, while tiny particles pass through you, one after another, each one too small to notice, each one carrying energy from distant parts of the universe. It's almost like standing in a gentle rain. You can't see or feel, but instead of water, it's energy. And instead of drops, it's particles moving faster than anything we experience in daily life. So why doesn't it affect us more on Earth? It comes back to that protection. The atmosphere absorbs much of it. The magnetic field redirects a lot of it. By the time radiation reaches the surface, only a small portion remains. It's like layers of glass filtering out bright light, making it safe to look at. Without those layers, the intensity would be much higher. And that's exactly what space is like. No filter, no barrier, just direct exposure, because nothing about radiation is visible. There's no color, no movement you can see, no sound, just a quiet presence always there. And maybe that's what makes it so fascinating, because it reminds us that not all dangers are obvious. Some are invisible, some are slow, some don't feel like anything at all, until much later. In space, danger isn't always about what you can see. Sometimes, it's about what you can't. And radiation is one of the clearest examples of that, a constant, silent part of the universe. Always moving, always present. Even in the quietest, most peaceful places, the sun feels familiar. It rises every morning, warms the ground, and lights up the sky. It's something we've known our entire lives. Steady, reliable, almost gentle, but the sun is not always calm. Beneath that steady glow, it is constantly moving, shifting, twisting, building energy over time. and sometimes it releases that energy all at once. These events are called solar flares. They are sudden bursts of energy from the surface of the sun, like a flash of light that spreads outward into space. But they're much more than just light. They carry radiation, and sometimes they send out streams of charged particles moving at incredible speeds. To understand how powerful this is, imagine the largest explosion you've ever seen in a movie. Now imagine something far beyond that. A solar flare can release as much energy as billions of nuclear bombs going off at the same time. It's hard to picture something that large. It would be like lighting up the entire Earth again and again in just a few moments. But here's the strange part. From Earth, we don't usually feel it. Why not? Because once again, we are protected. The atmosphere absorbs much of the radiation. The magnetic field redirects many of the charged particles. So most of the time, these powerful events pass by without affecting us directly. Sometimes they create beautiful effects, like the aurora, glowing lights in the sky near the poles, shifting colors like a slow, silent dance. But beyond that, life goes on as usual. So what happens in space? Without that protection, things are very different. If a solar flare sends radiation toward a spacecraft, it becomes a serious concern. This leads to what is often called a radiation storm, a wave of energetic particles traveling outward from the sun. These particles move extremely fast, not quite at the speed of light, but still fast enough to cross the distance between the sun and Earth in a matter of hours. Think about that. The sun is about 150 million kilometers away, roughly the distance you would travel if you drove around the Earth nearly 4,000 times. And yet, these particles can cover that distance in less than a day. So if astronauts are out in space, what happens when a radiation storm approaches? They can't see it coming in the usual way. There's no dark cloud, no visible wall moving toward them. Instead, they rely on instruments and monitoring systems. Scientists on Earth watch the sun closely, tracking its activity. If a flare is detected, warnings can be sent, but the timing is important. Sometimes there is enough notice, sometimes there is very little. So what can astronauts do? Inside a spacecraft, there are areas with extra shielding. You can think of them like small, safe zones, built to offer more protection during these events. When a radiation storm is expected, astronauts may move into these areas and stay there until it passes. It's a bit like taking shelter during a storm on Earth, except this storm is made of invisible particles instead of wind and rain. And instead of hearing thunder, there is only silence. This brings up an interesting question. If radiation is invisible, how do we know how strong it is? The answer is through measurement. Instruments can detect the energy levels and the number of particles passing through. It's like using a thermometer to measure temperature, but instead of heat, it measures radiation, and during a strong solar event, those readings can rise quickly. Now here's something many people don't realize. The sun goes through cycles. Roughly every 11 years, its activity increases and decreases. During more active periods, solar flares and radiation storms become more common. It's like the sun has quiet years and busy years. So space missions often take this into account. Planning becomes important. Timing matters, because being in space during a very active solar period can increase the risk. And yet, even with all this danger, the sun still appears calm from a distance, a bright circle in the sky, steady, unchanging. It doesn't look like something that could send powerful waves of energy across millions of kilometers, but that's part of what makes space so fascinating. Things don't always look as powerful as they are. A quiet surface can hide intense activity underneath. So, if a radiation storm passed through a spacecraft, would it be immediately noticeable? Not in the way you might expect. There wouldn't be a loud sound, no shaking, no visible impact. Instead, it would be detected through instruments. And over time, the increased radiation exposure would become the concern. Again, it's that same quiet pattern. Invisible, gradual, but real. This is why shielding and planning are so important. Because unlike something you can see or hear, radiation requires awareness in a different way. You have to trust the data, the measurements, the understanding of how space behaves, and maybe that leads to a deeper thought. The sun, something we depend on every day, is also capable of creating one of the most dangerous environments in space. It gives life, and at the same time, it can send out energy that challenges that life beyond Earth. But it doesn't do this with intention. It's simply following its nature. A star, constantly releasing energy, sometimes in quiet ways and sometimes in sudden bursts. So if you were out there, far from Earth, watching the sun, it might look peaceful, just a bright, glowing sphere. But at any moment, it could release a wave of energy that travels across space, reaching you hours later. No warning in the sky, no visible change, just a silent arrival of particles moving faster than anything we experience in everyday life. And once again, the pattern appears. In space, danger is often quiet, not dramatic, not obvious, but always present, waiting in ways we don't always expect. Even from something as familiar as the sun, some of the most powerful events in the universe don't look powerful at all. In fact, you wouldn't see them coming. No light growing brighter, no sound building up, no warning in the sky, just silence. And then, if you were in the wrong place at the wrong time, a wave of energy would pass through space with incredible force. These events are called gamma-ray bursts, and they are among the most energetic things we know. To understand how intense they are, imagine this. Our sun has been shining for billions of years. Every second, it releases a huge amount of energy, enough to light and warm the entire Earth. Now imagine all of that energy not spread out over billions of years, but released in just a few seconds. That's the scale we're talking about. A gamma-ray burst can release more energy in a few seconds than the sun will produce in its entire lifetime. It's like compressing something that lasts billions of years into a moment shorter than a breath. So what causes something like this? Usually, it happens when a very large star reaches the end of its life. The star collapses in on itself, and in that collapse, it creates a powerful explosion, or sometimes two incredibly dense objects, like neutron stars, collide. When that happens, the energy released is focused into narrow beams that shoot out into space, not in all directions, but in specific paths, like a flashlight beam. And that detail is important because it means most of these bursts never reach us. They happen somewhere in the universe, but their energy is pointed in another direction, so we don't feel them. We don't even notice them. But what if one of those beams were aimed directly at Earth? That's where things become more serious. Gamma rays are a form of radiation, but not like the kind we usually think about. They are much more energetic, much more intense. If you imagine regular light as a gentle glow from a lamp, gamma rays are like a concentrated beam of energy, packed tightly and moving fast. They can pass through matter more easily, carrying enough energy to affect atoms directly. So what would happen if a gamma-ray burst reached Earth? Fortunately, most of them happen very far away, millions or even billions of light years away. That distance makes a huge difference. By the time the energy reaches us, it has spread out and weakened. It's like hearing a loud sound from far away. It becomes faint and harmless, but if one happened closer and pointed directly at Earth, the effects could be much stronger. It could affect the upper atmosphere, changing its structure. It could increase radiation levels at the surface, not instantly destroying everything, but creating conditions that would be difficult for life. Now, here's an interesting question. If these events are so powerful, why don't we see them? The answer lies in their direction. Remember, the energy is focused into beams. If you're not in the path of the beam, you might not notice anything at all. It's like standing in a dark room while someone shines a flashlight in another direction. The light is there, but it doesn't reach you. So most gamma ray bursts happen quietly, unnoticed, somewhere far away. But when they are detected, it's through instruments. Satellites designed to watch the sky, picking up bursts of high-energy radiation. And when one is detected, scientists can study it, measure it, and learn more about these powerful events. But even then, they often appear as brief flashes, lasting seconds, sometimes even less. So something incredibly powerful happens very quickly, and then it's gone. That's another pattern in space. Extreme events that last only a moment, but carry enormous energy. So what would it feel like to be near one? That's difficult to imagine because they are so rare and so distant from us. But the key idea is this: you wouldn't see it coming. There wouldn't be a build-up, no gradual change, just a sudden arrival of energy, invisible, silent, and incredibly fast, because gamma rays travel at the speed of light, about 300,000 kilometers per second. Fast enough to circle the Earth more than 7 times in 1 second. So, by the time you could even think about it, it would already be over. And that leads to something interesting. Even though gamma ray bursts are among the most powerful events in the universe, they don't behave in ways we usually expect. They don't explode with sound. They don't create visible shockwaves you can watch from a distance. They simply release energy and send it across space, quietly, effortlessly. So why don't we worry about them more? Because the universe is very large. Distances between stars and galaxies are enormous, so the chances of a gamma ray burst happening close enough and pointed directly at Earth are extremely low. It's possible, but unlikely. And that distance acts like a kind of natural protection. The farther away something is, the more its energy spreads out before reaching us. It's like a drop of ink spreading in water. The farther it spreads, the less concentrated it becomes. So by the time most gamma ray bursts reach us, they are harmless, just faint signals picked up by instruments. But the fact that they exist at all is fascinating, because it shows just how powerful the universe can be. Events that release more energy than a star over billions of years, happening in seconds. And yet, from here, everything looks calm. The night sky appears steady. Stars twinkle gently. Nothing suggests that somewhere, far away, such powerful events are taking place. And maybe that's the most surprising part. The universe can hold these extreme events while still appearing peaceful, quiet, almost still, but hidden within that stillness are moments of incredible energy. Invisible waves traveling across vast distances, unnoticed, until they are measured and understood. And once again, we see the same idea. Space doesn't need to look dangerous to be dangerous. Sometimes, the most powerful things are the ones you can't see at all, just passing through, silently, across the endless dark. Space looks empty. When you see images of it, you notice the darkness, the stars, and the wide open space between them. It feels like there's nothing there. But that's not completely true. Even in that emptiness, there are tiny particles moving through space, all the time. Some are no bigger than grains of sand. Some are even smaller, like dust. you might see floating in a beam of sunlight. They are called micrometeoroids, and despite their size, they can be extremely dangerous. At first, that might sound surprising. How could something so small cause serious damage? To understand that, we need to think about speed. Here on Earth, we're used to objects moving at certain speeds. A car on a highway might go around 100 kilometers per hour. A fast train might go around 300 kilometers per hour. Even a bullet from a gun, which is very fast, travels at about 1,000 meters per second, roughly 3,600 kilometers per hour. That already sounds incredibly fast, but in space, micrometeoroids move much faster than that. They can travel at speeds of around 20,000 to 70,000 kilometers per hour. That's about 20 times faster than a bullet. Or imagine driving across an entire country in just a few minutes. That's the kind of speed we're talking about. So even though these particles are tiny, their speed gives them a lot of energy, and when something that fast hits an object, the impact becomes very powerful. Think about it like this. If you gently toss a grain of sand at a window, nothing happens. But if that same grain of sand were moving at tens of thousands of kilometers per hour, it would hit with enough force to damage the surface. It's like the difference between tapping on a glass and striking it with a hammer. Speed changes everything. So what happens if a micrometeoroid hits a spacecraft? It depends on the size and speed, but even very small particles can cause noticeable damage. They can leave tiny pits, like small dents on the surface. Over time, many of these impacts can wear down materials. And if a slightly larger particle hits, it can puncture the outer layer. That's why spacecraft are built with special shielding. Not just one layer, but often multiple layers designed to absorb and spread out the energy of an impact. You can think of it like wearing several layers of clothing. If something sharp hits, each layer slows it down a little more, reducing the chance that it reaches the inside. Some spacecraft use what's called a Whipple shield. It works in an interesting way. The outer layer is designed to break apart the particle when it hits. So, instead of one solid piece continuing inward, it turns into a small cloud of fragments. Those fragments then hit the next layer, spreading their energy over a wider area. This reduces the damage. It's a clever way to deal with something that's moving too fast to simply block with a single wall. Now, here's a question. If these particles are everywhere, why don't we see them? The answer is simple. They are too small, and space is too vast. Even though there are many particles, the distance between them is still large. So collisions don't happen constantly, but when they do happen, the speed makes them important. This is especially true for astronauts during spacewalks. When astronauts leave the safety of a spacecraft, they rely on their suits for protection. Spacesuits are designed to handle small impacts, but they still have limits. A very small particle might not cause serious harm, but a larger one, even if it's only the size of a tiny pebble, could be dangerous at those speeds. So spacewalks are carefully planned. Time is limited, and every movement is controlled, because even in a place that looks empty, there are still risks moving silently around. Now think about something else. On Earth, when something moves fast through the air, it creates sound, a rushing noise, a whistle. But in space, there is no air. So even if a micrometeoroid passes nearby at incredible speed, you wouldn't hear it. No warning, no sound at all. Just a silent object moving faster than anything we experience in everyday life. This creates a strange situation. You are surrounded by motion, but it feels completely still, and that stillness can be misleading because it makes space seem safer than it really is. So how often do these impacts happen? Small impacts happen fairly regularly over long periods. That's why satellites and spacecraft often show signs of tiny damage after spending time in orbit. It's like a car that has been on the road for years, collecting small chips and marks from debris. But in space, those marks come from particles moving at extreme speeds. Over time, engineers study this damage to improve designs. Better materials, stronger shielding, smarter ways to reduce risk, because even though micrometeoroids are small, they are part of a constant environment, always moving, always present. So if you were floating in space, surrounded by stars, everything might feel calm, still, quiet, but at the same time, tiny particles would be moving around you at incredible speeds, invisible, silent, and powerful in their own way. It's a reminder that size doesn't always determine danger. Something small can still carry a lot of energy, especially when it's moving fast enough. And in space, speed is everywhere. Objects travel freely, without air to slow them down. They keep moving, sometimes for millions of years, until they encounter something in their path. A spacecraft, a satellite, or anything else in orbit. And when they do, even a tiny piece of dust can leave a mark. So once again, space reveals something unexpected. It's not just the large, dramatic dangers we need to think about. Sometimes it's the smallest things, the ones you can't see, the ones that move quietly through the dark, carrying energy from distant places, across endless space, waiting for the moment they meet something in their path. If you look up at the night sky, everything seems still. Stars hold their positions. The moon moves slowly. There's a sense of calm, as if nothing is really happening above you. But closer to Earth, just beyond what you can see, there is a different kind of environment. It's not empty. In fact, it's becoming more crowded. Around our planet, there are thousands of objects moving at very high speeds. Some of them are active satellites, quietly doing their jobs, helping with communication, navigation, weather tracking, and more, but many of them are no longer in use. Old satellites, broken parts, fragments from past collisions, even tiny pieces left behind from launches. All of this is known as space debris, and it's growing over time. At first, this might not sound too serious. After all, space is huge. So how could a few broken objects become a problem? The answer, once again, comes down to speed. Just like micrometeoroids, space debris moves very fast. Objects in low Earth orbit travel at around 28,000 kilometers per hour. That's fast enough to circle the entire Earth in about 90 minutes. Imagine getting in a vehicle and traveling around the planet in the time it takes to watch a movie. That's how quickly these objects are moving. So even a small piece of debris can be dangerous. A fragment no bigger than a coin can hit with the force of something much larger, because at those speeds, energy increases dramatically. It's like the difference between gently tossing a pebble and firing it from a powerful launcher. Same size, but very different impact. So what happens if debris hits a satellite? It can damage it, disable it, or even destroy it completely. And when that happens, it creates more debris, more fragments, more pieces moving through orbit. This leads to an interesting and concerning idea. What if one collision leads to another, and then another? This is sometimes called a chain reaction. One event creating many smaller pieces, which then increase the chance of more collisions. Over time, this could make certain orbits more dangerous, more crowded, more difficult to use safely. So how do we deal with this? Space agencies around the world track debris. Using radar and telescopes, they monitor objects in orbit, especially the larger ones. If a piece of debris is on a path that could come close to a satellite or the International Space Station, adjustments can be made. Small movements, carefully planned to avoid a possible collision. It's a bit like traffic control. But instead of cars on roads, it's objects moving in 3 dimensions at extremely high speeds around an entire planet. Now here's a question. If debris is moving so fast, could you see it coming? In most cases, no. It would move too quickly, and many pieces are too small to detect without instruments. So again, we see the same pattern. Invisible motion, silent danger, things happening without any direct warning to the human senses. This is especially important for astronauts. Inside the International Space Station, there is protection, layers of shielding designed to handle small impacts. But even so, the station is carefully monitored. If there's a risk of a larger piece of debris passing nearby, astronauts may move into a safer area within the station. Sometimes, they prepare for the possibility of leaving quickly if needed, because even though the station is strong, the speeds involved make caution necessary. Now think about how this situation began. In the early days of space exploration, there were only a few objects in orbit, a handful of satellites, simple missions. Over time, more and more launches took place, each one adding new objects to space. Some stayed active, others stopped working, and pieces were left behind. It's a bit like a road that slowly becomes more crowded over the years. At first, it's empty. Then a few cars appear, then more. And eventually, traffic becomes something you have to manage carefully. But unlike roads, space doesn't have lanes or clear paths. Objects move in orbits, crossing paths at different angles and speeds, so managing this environment becomes more complex. And as technology grows, more satellites are being launched, especially for things like global internet coverage. This increases the number of objects in orbit even further. Which raises another question. Will space around Earth become too crowded? It's something scientists are actively working to prevent. New designs aim to reduce debris. Some satellites are built to burn up in the atmosphere at the end of their mission. Others are designed to move into safer orbits. There are even ideas for cleaning up debris, capturing it, and removing it from orbit. It's not simple, but it shows how important this issue has become. Because space near Earth is valuable, it's where many important systems operate, and keeping it safe is essential for the future. So if you were looking down at Earth from orbit, everything might seem peaceful. The planet below, covered in clouds and oceans, the blackness of space around you. But at the same time, objects would be moving all around you. Fast, silent, following paths, shaped by gravity. Some active, some no longer in use. All part of a growing environment that we can't see from the ground. And once again, the danger isn't loud or obvious. There's no sound of movement, no visible signs of speed, just quiet motion happening constantly. And that's what makes space around Earth so unique. It's not empty, it's active, filled with objects, each moving with purpose or simply continuing along a path set long ago. And among them, even a small piece can matter, because in space, speed gives even the smallest things the power to change everything, silently, quickly, and without warning. When we think about temperature, we usually imagine something steady, a warm afternoon, a cool evening, maybe a hot day that slowly turns into night. On Earth, temperature changes feel gradual. Even when it gets very hot or very cold, there's usually a transition. Air carries heat around, softening the extremes. But in space, things work very differently. There is no air to balance temperatures, no wind, no atmosphere to spread heat evenly. So instead of gradual changes, space is full of sharp contrasts. Very hot and very cold, existing right next to each other. This creates one of the most unusual environments you can imagine. Let's start with sunlight. If you're in space, and exposed directly to the sun, the heat can be intense. Surfaces can reach over 120 degrees Celsius. That's hotter than boiling water, the kind of heat that can cook food. If you've ever touched a metal surface left under strong sunlight, you know how quickly it heats up. Now imagine that effect, but stronger, with no air to carry the heat away. The sun's energy hits directly, and it stays there. But what happens if you move into the shadow, just a short distance away, where sunlight doesn't reach? Temperatures can drop to around -150 degrees Celsius. That's colder than the coldest places on Earth, colder than Antarctica during its harshest winters. So you have two extremes, side by side, hot enough to burn and cold enough to freeze, separated by just a small change in position. It's like standing with one foot in a fire and the other in deep ice. So why does this happen? It comes back to how heat moves. On Earth, air helps distribute heat. Warm air rises, cool air sinks, and everything mixes together. This creates a balance. But in space, there is no air to do that. Heat doesn't spread in the same way. It only moves through radiation, slowly transferring energy from one place to another. So if something is in sunlight, it keeps absorbing heat. If it's in shadow, it keeps losing heat. There's nothing to even things out. This leads to a natural question. If the temperature is so extreme, would you feel it instantly? Not exactly. Just like we talked about before, heat transfer in space is slower than we might expect. Even though the environment has extreme temperatures, your body doesn't immediately match those temperatures. It takes time. Your body holds on to its heat for a while. So if you moved from sunlight into shadow, you wouldn't instantly feel freezing cold. And if you moved into sunlight, you wouldn't instantly feel burning hot. There would be a delay, a gradual change. But over time, those extremes would begin to take effect, and without protection, they would become dangerous. This is why spacecraft and spacesuits have temperature control systems. They are designed to manage both heat and cold at the same time. You can think of it like a carefully balanced system, not too hot, not too cold, keeping everything within a safe range. Inside a spacecraft, temperatures are kept comfortable, similar to a room on Earth, but outside, the environment is constantly shifting between extremes. Now, think about something interesting. If an object is rotating in space, it experiences both sunlight and shadow over time. This means it heats up, then cools down, then heats up again. Over and over, this repeated cycle can be stressful for materials. They expand when heated, contract when cooled, and over time, this can cause wear and tear. It's like bending a piece of metal back and forth again and again. Eventually, it weakens. So engineers have to design materials that can handle these changes, strong enough to survive constant shifts between heat and cold. Because in space, there is no stable middle ground. It's always one extreme or the other. Now here's another question. What about planets and moons? Do they experience the same extremes? Many of them do. For example, the moon has no atmosphere, so during its daytime, the surface can become extremely hot, and during its nighttime, it becomes extremely cold. These changes happen over long periods, but the difference is still very large. Mars, on the other hand, has a thin atmosphere, so it can hold some heat, but not very well. Temperatures there can still vary widely. Warm in sunlight, very cold at night. Again, we see the same pattern. Without a thick atmosphere, temperature becomes unpredictable and extreme, and this shows us something important. On Earth, we often take temperature stability for granted. We expect things to stay within a certain range, comfortable, manageable, but in space, that stability doesn't exist. Everything depends on position, on whether you are facing the sun or hidden from it, on whether you are in light or shadow. So if you were floating in space, slowly rotating, you might experience both extremes over time, a gradual warming followed by a gradual cooling, back and forth, quietly, without any sound or warning. Just a slow shift in temperature, guided only by light and darkness. And once again, the danger isn't dramatic. There's no sudden moment, no loud signal, just the steady presence of extremes, waiting, changing, always there. Because space doesn't try to balance things. It doesn't smooth out the edges. It allows heat and cold to exist exactly as they are, and that creates an environment where even something as simple as temperature becomes a challenge, not because it changes quickly, but because it doesn't change in the way we expect. And in that difference, we begin to understand space a little more, a place where opposites exist, side by side, where heat and cold are not blended together, but separated, waiting for anything that passes between them. There is something we depend on every moment, without even thinking about it. Breathing. It feels automatic. You don't remind yourself to do it. You don't plan it. It just happens, quietly, in the background of everything else. Each breath brings in oxygen, and that oxygen moves through your body, carried by your blood, reaching every part that needs it. Your brain, your muscles, your organs, all of it depends on a steady supply. But what happens when that supply suddenly stops? In space, there is no oxygen to breathe. Not a little, not a thin amount, but none at all. And this creates one of the fastest and most serious dangers. Because without oxygen, the human body begins to shut down very quickly. So how fast does this happen? Faster than most people expect. If you were suddenly exposed to space, you would likely remain conscious for about 10 to 15 seconds. That's about the time it takes to take a few calm breaths or to walk across a small room. After that, you would lose consciousness. And here's something important. It wouldn't feel like drowning. That's a common misunderstanding. When people think about lack of oxygen, they imagine struggling, gasping, a feeling of panic. But in this case, it's different. Why? Because in space, there is no air to breathe in the first place. So there's no resistance, no water blocking your lungs, just emptiness. And that emptiness changes how the body reacts. Instead of a long struggle, it becomes a quiet, rapid process. So what would you actually feel? At first, you might try to take a breath, but there's nothing there, no air entering your lungs. And then, within seconds, the oxygen, already in your bloodstream, begins to run out. Your brain starts to notice the change, but not in a dramatic way. There might be a brief moment of confusion, a slight dizziness. Your vision might begin to narrow, like looking through a tunnel. Colors could fade, edges soften, and then very quickly, awareness slips away. It's not loud, it's not sudden. It's more like a dimming light, gradual but fast, and then nothing. Now this leads to a natural question. Why does the brain react this way? The brain is one of the most oxygen-dependent parts of the body. It uses a lot of energy, even when you're resting. You can think of it like a device that's always running, always processing information. And oxygen is what keeps it powered. Without it, the brain can't maintain its activity. So it begins to shut down, not all at once, but in stages. First, higher functions begin to fade. Thinking becomes slower. Then, more basic functions are affected. And finally, consciousness is lost. All of this happens in a very short time. Which raises another question. If someone were rescued quickly, could they recover? In some cases, yes. If oxygen is restored within a short window, the brain can recover. But that window is limited. After a few minutes without oxygen, the risk of permanent damage increases because brain cells are very sensitive. They need a constant supply. So even though the initial loss of consciousness happens quickly, the longer-term effects depend on how long the body remains without oxygen. Now think about how quiet this process is. There's no sound, no visible sign from the outside, just a person becoming still, unaware. It's one of the most silent dangers in space. No warning signal, no clear moment where you realize what's happening, just a gradual fading. And maybe that's what makes it so different from other dangers. It doesn't feel aggressive. It doesn't feel like something is attacking you. It simply removes something essential. And without that, the body can't continue. So how do astronauts protect themselves? Spacesuits and spacecraft are designed to provide a constant supply of oxygen, carefully controlled, balanced with pressure and temperature. It's not just about having air, it's about having the right conditions for the body to function. Inside a spacesuit, oxygen flows steadily. Carbon dioxide, the gas you breathe out, is removed. Everything is managed so that breathing feels normal, as if you were still on Earth. But outside that system, there is nothing, no backup, no natural source, just empty space. This is why even a small problem with a spacesuit or spacecraft becomes serious. A leak, a failure in the system, anything that interrupts the flow of oxygen, because time becomes very limited. Seconds, not minutes. And this brings us back to something simple. Breathing is easy to overlook. It's quiet, constant, always there, until it isn't. And in space, that difference becomes very clear. The line between having oxygen and not having it is immediate. There's no gradual transition, no warning, just presence or absence. And that absence changes everything. So if you were floating in space, surrounded by stars, everything might look calm, peaceful, still. But inside your body, a silent process would begin the moment oxygen is gone. A countdown, measured not in sound or motion, but in seconds of awareness. And once again, the danger isn't something you can see. It's not something you can hear. It's something you only notice when it's already happening, because in space, the most important things are often invisible. And oxygen is one of them, always present on Earth, completely absent beyond it. And in that absence, we begin to understand just how important it really is. When people imagine space, they often think about physical danger. No air, extreme temperatures, radiation. All of these are real, and all of them are important. But there is another kind of danger that is quieter, less visible, and sometimes just as powerful. It's the effect of being alone. In space, isolation is not just about being physically separated from others. It's about distance, silence, and the feeling of being very far from everything familiar. So what does that actually feel like? Imagine being in a place where you can't step outside, where every movement is inside a small, controlled environment, a space no larger than a small apartment, sometimes even smaller. Now imagine staying there not for a few hours, but for days, weeks, or even months. That's part of what astronauts experience. The International Space Station, for example, is about the size of a large house. Not tiny, but not very big either. Now imagine living in that space continuously. No fresh air from outside, no natural environment, just machines, equipment, and a few other people. It's like being inside a moving room, orbiting Earth every 90 minutes. So the question becomes, how does the mind respond to that? At first, it might feel exciting, new, interesting, but over time, the experience can change, because the human mind is used to variety, different places, different sounds, different people. In space, those changes are limited. The environment stays mostly the same. The routine becomes very structured. Wake up, work, eat, sleep, repeat. And while routine can be helpful, too much of it can begin to feel repetitive. Now think about distance. If you're on Earth and you feel isolated, you can usually change that. You can step outside, call someone, visit a different place, but in space, those options are limited. You can communicate with people on Earth, but there's often a delay, sometimes just a second or two, sometimes longer, depending on how far you are. It may not sound like much, but even a small delay changes the feeling of conversation. It makes things feel slightly less immediate, less connected. And if you travel farther, to places like Mars, that delay could grow to several minutes. Imagine asking a question and waiting minutes for a reply. It's like having a conversation where each response comes long after the moment has passed. So how does that affect someone over time? It can create a sense of separation, a feeling of being disconnected from everything you know. Now add to that the idea of confinement. You can't go outside, not without a spacesuit. And even then, it's not a casual experience. Every movement is planned. Every step is controlled. So most of the time, you remain inside, in the same environment, with the same surroundings. And over time, the mind begins to notice that small things can start to feel bigger. Minor annoyances can feel more important because there are fewer distractions, fewer changes to shift your focus. This is why astronauts are carefully selected and trained, not just for physical ability, but for psychological strength. They learn how to manage stress, how to work as a team, how to stay calm in a limited environment. Because being in space isn't just about surviving physically, it's also about staying mentally balanced. Now here's an interesting question. Do astronauts ever feel lonely? The answer is yes, sometimes. Even though they are often with a small team, the distance from Earth can still create a sense of loneliness. It's not the same as being alone in a room. It's more like being far away from everything familiar. Family, friends, everyday life. All of it becomes distant, and while communication helps, it doesn't fully replace being there in person. So how do astronauts cope with this? They stay connected in different ways: video calls, messages, sharing moments with people back on Earth. They also bring personal items, photos, small objects that remind them of home. These things help create a sense of connection, even in a place that feels very different. Routine also plays a role. Having a structured day helps keep the mind focused. It gives a sense of purpose, something to work toward, and that can make a big difference. Because purpose helps reduce the feeling of isolation. Now think about something else. In space, the view outside is vast, endless. The Earth below, slowly turning. Stars in every direction. It's beautiful, but also a reminder of distance. A reminder of how far away everything is. Some astronauts describe a feeling called the overview effect, a shift in perspective when seeing Earth from space, a sense of connection to the planet as a whole. But at the same time, there can also be a feeling of separation, because you're no longer part of that world in the usual way. You're observing it from a distance, and that distance can feel both amazing and isolating. So the psychological challenge of space is not just about being alone. It's about being far away, in a place where everything is controlled, where change is limited, where connection exists, but feels different. And once again, the danger is quiet. There's no sudden moment, no clear signal, just a gradual effect on the mind over time, slowly, subtly. Because the human mind is designed for a world with variety, connection, and movement. And space offers something very different: stillness, repetition, distance. So if you were living in space, surrounded by silence, floating above the Earth, everything might look calm, peaceful, almost perfect. But inside, your mind would be adjusting, adapting, finding ways to stay balanced in a place that feels both close and very far at the same time. And that balance becomes just as important as any physical protection, because in space, survival isn't only about the body. It's also about the mind, quietly working to stay steady, in a place where everything else feels so distant. On Earth, your body is always working against something, gravity. It's a constant force, gently pulling you downward every moment of your life. You don't notice it most of the time, but your body does. Your bones support your weight, your muscles keep you upright. Even when you're standing still, your body is making small adjustments to stay balanced. Now imagine that force suddenly disappears. In space, there is microgravity. This doesn't mean there is no gravity at all, but it feels like weightlessness. You float instead of stand. You drift instead of walk. And at first, that might sound comfortable, effortless, like your body finally gets to rest. But something interesting begins to happen over time. Without gravity, your bones no longer need to support your weight, so your body starts to change. Bones are living tissue. They are constantly being rebuilt. Old bone is broken down and new bone is formed. On Earth, this process stays balanced because your bones are under regular stress. Walking, standing, even sitting, these activities all send signals to your body that your bones need to stay strong. It's like a structure that is used every day. Because it's used, it's maintained. But in space, that stress is gone. Your body begins to think, I don't need to keep these bones as strong. And slowly, it starts to reduce bone density. This means your bones become weaker over time. Not instantly, not dramatically, but gradually, day by day. Now here's a question. How much bone loss are we talking about? Astronauts can lose about 1% to 2% of their bone density each month in space. To picture that, imagine a solid piece of wood slowly becoming lighter and less dense over time. It still looks the same from the outside, but inside, it's not as strong as it used to be on Earth. Losing that much bone density would take years. In space, it happens much faster. So what parts of the body are affected the most? Mainly the bones that normally carry weight, the legs, the hips, the spine. These areas are used to supporting your body against gravity. When that need disappears, they are affected the most. Now think about what happens when astronauts return to Earth. Suddenly, gravity is back. Their bones have to support weight again, but they are weaker than before. This can make simple things feel difficult at first. Standing, walking, even maintaining balance. It's like trying to use a structure that hasn't been under load for a long time. It needs time to adjust. So how do astronauts prevent this? They exercise every day, even in space. Special equipment is used to simulate resistance. Since there's no weight, they can't just lift heavy objects in the usual way. Instead, they use machines that create force in other ways. Pulling, pushing, creating tension. It's like working out with invisible weights. The goal is to keep the bones under stress, so the body continues to maintain them. Even with this, some bone loss still happens, but exercise helps reduce it. It slows the process. Now here's something interesting. This effect isn't just about space, it also teaches us something about life on Earth. When people don't use their muscles or bones for long periods, similar changes can happen. For example, if someone stays in bed for a long time without movement, their bones and muscles can weaken. It's not as fast as in space, but the principle is the same. The body adapts to what it experiences. If something isn't used, it begins to fade. So in a way, space exaggerates something that already exists. It shows us how important movement and gravity are for keeping the body strong. Now imagine floating in space for months. Your body feels light, effortless. You can move with just a small push, no pressure on your legs, no need to stand. At first, it might feel freeing, but beneath that feeling, your body is quietly changing. Bones becoming less dense, strength slowly decreasing, all happening without any immediate sensation. You wouldn't feel your bones getting weaker. There's no direct signal, no pain or discomfort in the moment. It's a gradual process, just like many other effects in space. So what happens after long missions? Astronauts go through rehabilitation. They work to rebuild strength, to restore bone density, to adjust back to life under gravity. And this takes time, because the body needs to readjust, to remember what it's like to carry weight again. Now think about future missions. Traveling to Mars, for example, could take many months. Astronauts would spend a long time in microgravity, so scientists are always looking for better solutions, better exercise systems, new ways to protect bone health, because maintaining the body becomes a major challenge during long journeys. And once again, we see something important. The danger in space isn't always immediate. It's not always something that happens in seconds. Sometimes, it's something that develops slowly, over days, weeks, months, a quiet change that only becomes noticeable over time. So if you were living in space, floating freely, everything might feel easy, light, effortless. But inside your body, a process would be unfolding. Bones adjusting to a new environment, responding to the absence of gravity, and that absence, something we never think about on Earth, becomes a powerful force in its own way. Because gravity doesn't just hold you down, it keeps your body strong. And without it, even something as solid as bone begins to change, slowly, quietly, until you return and feel its absence in a completely different way. On Earth, your muscles are always working. Even when you feel like you're resting, they are still active in small ways, standing upright, holding your head steady, keeping your posture balanced. Every movement, even a simple step, requires your muscles to push against gravity. Now imagine that force disappearing. In space, there is no need to push against your own weight. You don't have to stand, you don't have to walk, you don't even have to hold yourself upright. Instead, you float. And at first, that feels easy, almost effortless. You can move with just a gentle push. A small motion sends you drifting across the room. It might feel like your body has become lighter than ever before, but something begins to change. Because your muscles are no longer being used in the same way, the body starts to notice this, and it begins to adapt. Muscles, like bones, respond to how they are used. If they are used often, they stay strong. If they are not used, they begin to weaken. This process is called muscle atrophy, and in space, it can happen surprisingly quickly. So how fast does this happen? Within just a few days, the body begins to lose muscle strength. Over weeks, the changes become more noticeable, and over months, muscles can become much weaker if they are not actively maintained. To picture this, imagine a rubber band. When it's new, it's tight and strong, but if it's left unused for a long time, it can become loose and less responsive. Muscles behave in a similar way. Without regular use, they lose strength and size. Now think about which muscles are affected the most. Just like with bones, the muscles that normally work against gravity are the ones that change the most. The legs, the lower back, the core. These are the muscles that keep you standing and moving on Earth. But in space, you don't need them in the same way. so they begin to weaken. This leads to an interesting question. If floating is so easy, why does muscle strength matter? The answer becomes clear when astronauts return to Earth. Suddenly, gravity is back. Their bodies have to support weight again. But their muscles are no longer as strong as before. Simple actions can feel more difficult. Standing up, walking, even lifting something light. It's like using a tool that hasn't been used in a long time. It still works, but not as well. So how do astronauts prevent this? They exercise every day, even in space. Just like with bone health, special equipment is used. Since there are no weights to lift, machines create resistance in other ways. Pulling against straps, pushing against force, using devices that simulate the feeling of lifting. It's like creating artificial gravity for the muscles, and this is not optional. Exercise is a key part of daily life in space. Without it, muscle loss would happen much faster. Even with exercise, some weakening still occurs, but it is reduced, managed, kept under control as much as possible. Now here's something interesting. This effect is not unique to space. On Earth, if someone stops using certain muscles, those muscles also weaken. For example, if you stay in bed for a long time without moving, your muscles begin to lose strength. Athletes know this well. If they stop training, their performance decreases over time. The body adapts to what it does regularly. So in space, the absence of gravity removes one of the main reasons for muscles to stay strong, and the body responds by adjusting. Now imagine floating for weeks, moving effortlessly, never needing to push against your own weight. It might feel relaxing, almost like your body is always at rest. But beneath that feeling, your muscles are slowly changing, becoming less active, less engaged, and over time, less strong. You wouldn't feel this happening in the moment. There's no immediate signal, no sudden change, just a gradual shift, day by day. Now think about balance. On Earth, your muscles work together to keep you stable. Small adjustments happen constantly, even when you're standing still. But in space, that need disappears. There is no up or down in the usual sense. So the body doesn't practice balance in the same way. This can make returning to Earth even more challenging, because it's not just strength that needs to come back. It's coordination, timing, the ability to adjust to gravity again. So after long missions, astronauts go through rehabilitation. They rebuild strength, they retrain their muscles, they allow their bodies to adjust back to Earth's conditions. And this takes time, because the body has been living in a completely different environment. Now think about future space travel. Long missions to places like Mars could last many months. During that time, muscle atrophy becomes an even bigger concern. So scientists are always exploring new ideas, better exercise systems, artificial gravity concepts, ways to keep the body strong over long periods. Because maintaining muscle strength is not just about comfort, it's about survival, being able to move, to react, to function properly in different environments. And once again, we see a pattern. Space doesn't always create sudden danger. Sometimes, it changes the body slowly, quietly, in ways that are not immediately noticeable. So if you were living in space, floating through a silent environment, everything might feel easy, light, effortless. But inside your body, your muscles would be adapting, responding to a world without gravity, letting go of strength that is no longer needed. And that's what makes space so unique. It doesn't just challenge the body with extremes. It changes how the body works over time, in ways that are gentle but powerful, because even something as simple as movement depends on gravity, and without it, the body begins to rewrite its own rules, slowly, quietly, until you return and feel the difference all at once. On Earth, Your body is shaped by gravity in ways you rarely notice. Fluids inside you, like blood and water, are gently pulled downward. This creates a natural balance. More fluid tends to stay in your lower body, especially in your legs and feet. It's part of why your feet can feel tired after standing for a long time. Gravity is always guiding where things settle, but what happens when that pull is no longer there? In space, that downward force disappears, and when it does, fluids inside your body begin to move. Not outward, not away, but upward toward your head. At first, this might sound like a small change, but it affects the body in noticeable ways. Astronauts often describe a feeling of fullness in their face, as if pressure has built up. Their faces can look slightly puffier than usual, and at the same time, their legs can appear thinner. Because fluid has shifted away from them, it's almost like redistributing water inside a container. If you tilt the container, the water moves to a new position. In space, the tilt comes from the absence of gravity, so everything settles differently. Now here's a question. If fluid moves toward the head, what does that feel like? Some astronauts compare it to having a mild cold, a sense of pressure in the sinuses, a feeling of congestion, but without the discomfort of illness. It's just a new sensation, one that the body isn't used to. Over time, the body begins to adjust. It tries to find a new balance. But the effects don't stop at the face. Fluid shifts also affect the eyes, and this is where things become more important. Inside the head, increased fluid can change pressure around the eyes and brain. For some astronauts, this can lead to changes in vision, blurriness, difficulty focusing. It's not the same for everyone, but it's something that has been observed during long missions. So why does this happen? Think of the body like a system that has been designed for one environment. Earth. All its processes are built around gravity. When that environment changes, the system has to adapt. But adaptation isn't always perfect. Some changes work smoothly. Others create new challenges. Fluid movement is one of those challenges. Now imagine floating in space for days, weeks, months. At first, the shift feels noticeable, a new sensation in your head, a different feeling in your body. But over time, it becomes normal. Your body accepts it as the new state. This leads to an interesting idea. The human body is very flexible. It can adapt to new environments, but that adaptation comes with trade-offs. Changes that make sense in one environment may not be ideal in another. So when astronauts return to Earth, gravity comes back into play. Fluids begin to move downward again, back to their original distribution. But just like with muscles and bones, this adjustment takes time. The body has to readjust, to remember what it's like to function under gravity. Now think about how important fluid balance is. Blood carries oxygen and nutrients. It supports every part of the body. Even small changes in how it moves can affect how the body feels and functions. So managing these changes becomes an important part of space travel. Scientists study fluid shifts carefully. They look for ways to reduce their effects, to protect vision, to maintain balance in the body. Because as missions become longer, these changes become more significant. Now here's another question. If fluid moves upward, does that affect how the heart works? Yes, in some ways. The heart doesn't have to work as hard to move blood upward, because there is no up in the usual sense. So over time, the cardiovascular system can also adapt, becoming slightly less strained. But again, this creates a challenge when returning to Earth, because gravity returns, and the body has to readjust once more. So even something as simple as fluid movement becomes part of a larger picture, a chain of changes, each one connected to the absence of gravity. Now imagine floating quietly in space. No weight, no pressure pulling you down, everything feels balanced, but in a different way. Inside your body, fluids are shifting, settling into new patterns. Your face feels fuller, your legs feel lighter, your body is learning a new version of itself, and all of this happens without any sound, without any visible signal from the outside, just a quiet adjustment, a slow shift in how your body organizes itself. It's another example of how space changes things in subtle ways, not always dramatic, not always immediate, but steady, constant. And over time, those small changes become important because they affect how you see, how you feel, how your body functions as a whole. So if you were living in space, surrounded by silence, drifting gently, everything might feel calm, but inside, your body would be quietly rearranging itself, adapting to a world without up or down, learning to function in a place where even fluids no longer follow the same rules. And that's what makes space so fascinating. It doesn't just change what's around you, it changes what's inside you too, in ways that are easy to overlook, but impossible to ignore over time. When you look at the moon from Earth, it feels calm, a soft glow in the night sky, smooth, quiet, almost peaceful. It doesn't look dangerous. It doesn't look extreme. But standing on the moon would feel very different, because the moon is not a gentle place. It's a world of sharp contrasts, hidden challenges, and constant exposure. Let's start with something simple. The ground. You might imagine it as soft dust, like sand on a beach, and it is dusty, but not in the way we used to. The surface is covered in very fine particles, created over billions of years by tiny impacts. These particles are not smooth. They are sharp, jagged, more like tiny shards than soft grains. If you could look at them up close, they would resemble broken glass more than beach sand. So what does that mean? It means the dust can cling to surfaces easily. Spacesuits, equipment, anything that touches it. And because the particles are sharp, they can cause wear over time. It's like rubbing something with very fine sandpaper again and again. Small damage builds up slowly. Now think about walking on that surface. Astronauts don't walk the same way they do on Earth. The moon's gravity is about 1/6 of Earth's. That means you would weigh much less. If you weigh 60 kilograms on Earth, you would feel like only 10 kilograms on the moon. It's like carrying a heavy bag on Earth, and suddenly it feels almost weightless. So movement becomes different, more like hopping or bouncing than walking. At first, that might feel fun, light, almost playful, but it also makes control more difficult. Each step needs to be careful, because you move farther with less effort. Now let's think about temperature. The moon has no atmosphere, no air to hold heat, no layer to soften temperature changes. So when the sun shines on the surface, it becomes extremely hot. Around 120 degrees Celsius, hot enough to boil water, hot enough to heat metal very quickly. But when the sun is not shining, the temperature drops sharply, down to around -170 degrees Celsius. That's colder than the coldest natural temperatures on Earth. So the difference between day and night is extreme. It's like switching from a hot oven to a deep freezer. And these changes don't happen gradually. They follow the long day-night cycle of the moon. About 14 Earth days of sunlight, followed by 14 days of darkness. 2 weeks of heat, 2 weeks of cold. So how do astronauts deal with this? Spacesuits are designed to handle both extremes. They regulate temperature, protecting the body from both intense heat and deep cold. Inside the suit, conditions remain stable, but outside, the environment is constantly shifting. Now here's another question. What about radiation? On Earth, we are protected by the atmosphere and magnetic field. But the moon has neither, so radiation reaches the surface more directly, from the sun, from space. This means astronauts are exposed to higher levels of radiation during their time there, so missions are carefully planned to limit exposure. Time becomes important again, just like in other parts of space. Now think about something else. The sky on Earth. The sky is blue during the day, filled with light scattered by the atmosphere. On the moon, there is no atmosphere, so even in daylight, the sky is black, completely black. Stars would still be there, though harder to see in bright sunlight, and the sun would appear as a sharp, bright disk, unfiltered, intense. It's a strange combination. Bright ground, black sky, no clouds, no color in the air, just light and shadow. And those shadows are very dark, because there's no air to scatter light into them, so areas not directly lit by the sun become almost completely black. This creates sharp contrasts, bright surfaces right next to deep darkness. Now imagine standing there. The ground beneath you is rough and dusty. The horizon feels closer because the moon is smaller than Earth. Mountains and craters stretch across the surface, and above you, a black sky, no sound, no wind, nothing moving unless you move it. It's completely still, and that stillness can feel unusual, because on Earth there's always some kind of background, wind, birds, distant sounds. On the moon, there is none of that, just silence, and that silence is constant. Now think about how long the moon has been this way. Billions of years, unchanged. No weather to reshape the surface, no rain to smooth it out. Every mark stays. Footprints left by astronauts during past missions are still there, untouched. It's like a place where time moves differently, where changes happen very slowly. So what makes the moon dangerous? It's not one single thing, it's the combination. Extreme temperatures, sharp dust, radiation, low gravity, and complete exposure to space. Each one manageable with the right protection. But together they create a challenging environment, one that requires constant attention, careful planning, and strong equipment. So if you were standing on the moon, looking back at Earth, everything might feel calm, the view would be beautiful, the silence complete, the surface still, but around you, the environment would be unforgiving. Not because it's violent, but because it offers no protection, no comfort, no natural support for life. And once again, we see the same idea. Space and places like the moon are not actively dangerous. They don't try to harm. They simply exist as they are. And in that state, survival depends entirely on what you bring with you, because beyond Earth, safety is not given. It is created, carefully, deliberately, one system at a time, in a place where even the ground beneath your feet tells a very different story than it does at home. Mars is often called the next step, a place people imagine visiting, maybe even living on one day. When you see pictures of it, the surface looks familiar in some ways. Mountains, valleys, wide open landscapes. It almost feels like a distant version of Earth, but that feeling can be misleading, because Mars, despite its similarities, is still a very dangerous place. Let's begin with the air. On Earth, the atmosphere is thick enough to breathe, and it protects us in many ways. On Mars, the atmosphere is very thin, about 100 times thinner than Earth's. To picture that, imagine standing on the highest mountain on Earth, where the air is already hard to breathe. Now imagine the air being even thinner than that, so thin that you couldn't survive without support. There is oxygen on Mars, but only in very small amounts, not nearly enough to breathe, so astronauts would need spacesuits or controlled habitats, just like in space. Without them, survival would only last a short time. Now think about pressure. The thin atmosphere also means very low pressure, similar to what we talked about earlier with space, though not completely the same. It's low enough that it still creates serious challenges for the human body. So even though Mars has an atmosphere, it doesn't provide the protection we are used to. It's more like a very light layer, not enough to rely on. Now let's talk about temperature. Mars is cold. On average, the temperature is around -60 degrees Celsius. That's colder than a typical freezer. But it doesn't stay the same. During the day, near the equator, temperatures can rise to around 20 degrees Celsius. That's like a mild day on Earth, but at night, it can drop back down to -100 degrees Celsius or lower. So just like the Moon, Mars has large temperature changes, warm for a short time, and then very cold again. Now, here's an interesting question. If Mars has an atmosphere, why doesn't it hold heat better? The answer is its thickness. Earth's atmosphere traps heat, keeping temperatures more stable. Mars' atmosphere is too thin to do that effectively, so heat escapes quickly. Now think about radiation. Mars does not have a strong magnetic field like Earth, and its atmosphere is too thin to block much radiation. So the surface is exposed to higher levels of radiation, similar to being in deep space, though slightly reduced. Over long periods, this becomes a serious concern for human missions. Protection becomes essential. Dust. Mars is known for its dust storms, and these are not small events. They can cover large areas of the planet, sometimes even the entire planet. Imagine a storm that doesn't just cover a city or a country, but spreads across a world. These storms can last for weeks or even months. The dust is very fine, similar in some ways to the Moon's dust, and it can affect equipment, cover solar panels, reduce visibility, create challenges for machines and habitats. Now you might wonder, if the atmosphere is so thin, how can it create such large storms? The answer is the scale of the planet and the behavior of the dust. Even with low pressure, wind can still move particles across vast distances, and once the dust is lifted, it can stay suspended for a long time, creating a hazy environment that spreads slowly but widely. Now think about gravity. Mars has about 1/3 of Earth's gravity, so if you weigh 60 kilograms on Earth, you would feel like about 20 kilograms on Mars. Heavier than on the Moon, but still much lighter than on Earth. This changes how you move, how you walk, how your body feels over time. It's easier to lift things, easier to move, but it also affects the body in ways similar to microgravity, though not as extreme. Long-term effects are still being studied. Now imagine standing on Mars. The sky would look different, not deep blue like Earth, more of a soft reddish tone, influenced by the dust in the atmosphere. The sun would appear smaller, less bright than it does from Earth, and the landscape would stretch out in shades of red and brown. Rocky, dry, quiet. There would be no sound of wind in the way we hear it on Earth. Because the atmosphere is so thin, sound doesn't travel as well. Everything feels more muted, more distant. Now think about water. Mars once had flowing water, rivers, lakes, maybe even oceans. But today, most of that water is gone or frozen, locked beneath the surface, or in ice. So any mission to Mars would need to bring or produce water. Another challenge to manage. So what makes Mars dangerous? It's not just one factor. It's everything combined. Thin air, low pressure, cold temperatures, radiation, dust storms, limited resources, each one manageable with the right technology. But together, they create a complex environment, one that requires constant planning and support. Mars feels closer to Earth than most other places in the solar system. More familiar, more reachable. But that familiarity can hide how extreme it really is. Because even though it looks like a place we could stand on, it is still far from being naturally safe. So if you were standing there, looking across the red landscape, everything might seem calm, still, quiet, almost peaceful. But beneath that calm, the environment would be challenging every part of your survival, not with sudden danger, but with constant conditions that require protection. And once again, we see the same idea. Space and the worlds within it are not built for us. They don't provide what we need. They simply exist as they are, and any life there must bring its own safety, create its own balance, in a place where even the air itself is not something you can rely on. And that is what makes Mars both fascinating and dangerous at the same time. When you look at planets like Jupiter or Saturn, they appear smooth, large, almost soft in appearance, with swirling colors and gentle bands wrapping around them. They don't look solid in the way Earth or Mars does, and that's because they aren't. These planets are called gas giants. They are made mostly of gas and liquid, not solid ground. So what would happen if you tried to land on one? At first, it might seem like you could simply descend through the clouds, like falling into a thick sky. No hard surface, no sudden landing, just a gradual journey downward. But that idea hides something much more serious. Because as you go deeper, the environment changes rapidly. Let's begin with gravity. On Earth, gravity pulls you downward with a steady force. It feels normal, something you're used to. On Jupiter, gravity is much stronger, about 2.5 times stronger than Earth's. So if you weigh 60 kilograms on Earth's, you would feel like about 150 kilograms on Jupiter. That's like carrying 2 extra people on your shoulders all the time. Just standing would feel heavy. Moving would require much more effort. Now imagine going deeper into the planet. Unlike Earth, where gravity decreases as you go toward the center, gas giants have layers that behave differently. As you descend, the pressure increases very quickly, because above you, there is more and more material pressing down. It's like being underwater. The deeper you go, the more water is above you, and the greater the pressure becomes. But instead of water, it's layers of gas and liquid, and the scale is enormous. Jupiter is so large that more than 1,300 Earths could fit inside it. Imagine stacking 1,300 Earths together to match its size. That's how massive it is. So the amount of material above you as you descend becomes immense. And with that comes pressure. At first the clouds might seem gentle, soft like mist or fog. But as you go deeper, the atmosphere becomes denser, thicker, more like a fluid, and the pressure rises. How strong does that pressure become? It becomes extreme, much stronger than anything we experience on Earth. If you've ever dived into deep water, you might feel pressure in your ears. Now imagine going much deeper, so deep that the pressure feels like having hundreds of cars stacked on top of you, then thousands, then more. At some point, no material we know could withstand it. Not a spacecraft, not a human body. Everything would be compressed, crushed, but not in a sudden way. It would happen gradually as you descend. The deeper you go, the more intense it becomes. Now think about temperature. Just like pressure, temperature also increases as you go deeper. At the upper layers, it might be relatively cold, but deeper inside, temperatures rise to extreme levels, hot enough to melt materials, hot enough to change the state of matter itself. So as you move downward, you are not only dealing with increasing pressure, but also increasing heat. This combination creates an environment that becomes more hostile with every step. Now here's something interesting. There is no clear surface on a gas giant. No ground you can stand on. No solid point where you can say, "This is the surface." Instead, the atmosphere gradually becomes denser. Gas turns into liquid-like states, and deeper still, it becomes something even more unusual. For example, on Jupiter, scientists believe that hydrogen, the most common element, is compressed so much that it behaves like a metal. Liquid metallic hydrogen, a form of matter that doesn't exist naturally on Earth. So instead of landing, you would be sinking continuously with no stopping point. Now imagine what that would feel like. You begin in the upper atmosphere, floating among clouds, gravity already stronger than Earth's. Then slowly you descend. The air becomes thicker, harder to move through. Pressure builds. Your body feels heavier, then heavier still. The temperature rises, the environment becomes more intense, and there is no solid ground to reach, only deeper layers, each one more extreme than the last. Now think about storms. Gas giants are known for their massive storms. Jupiter, for example, has a storm called the Great Red Spot. It's been active for hundreds of years, and it's so large that Earth itself could fit inside it. Imagine a storm big enough to swallow the entire planet you live on. That's the scale we're talking about. Winds in these storms can reach hundreds of kilometers per hour, some even faster. So even before reaching deeper layers, the upper atmosphere is already dynamic, powerful, constantly moving. Now this raises a question. If gas giants are so dangerous, why do they look so calm? From a distance, the clouds appear smooth. The colors blend gently. There's no visible chaos from far away. But up close, the reality is very different. Movement, pressure, heat, all working together in a complex system. And once again, we see the same pattern. What looks calm from afar can be incredibly intense up close. So if you were approaching a gas giant, it might seem inviting at first, beautiful, almost peaceful. But as you get closer, the scale becomes clear. The size, the gravity, the depth, and the realization that there is no safe place to stand, no solid ground to return to. Only layers that become more extreme as you go deeper. And in that descent, everything changes. Slowly, steadily, until the environment becomes too much to withstand, because in space, not all dangers are sharp or sudden. Some are deep, endless, and impossible to escape once you move too far in, and gas giants are a perfect example of that. Worlds where the deeper you go, the more intense everything becomes, with no clear end and no solid place to rest. When you think about wind, you might imagine something familiar. A gentle breeze moving through trees, a strong gust pushing against you on a stormy day, something you can feel on your skin, something you can hear as it passes by. But on Neptune, wind is something else entirely. It is faster than anything we experience on Earth, stronger, more extreme, and at the same time, strangely quiet. Neptune is one of the farthest planets from the Sun, so you might expect it to be calm, cold, and still, a place where nothing moves very quickly. But that's not what happens. Instead, Neptune has some of the fastest winds in the entire solar system, reaching speeds of over 2,000 kilometers per hour. To picture that, imagine a passenger airplane flying through the sky. Now imagine something moving at twice that speed, or think about a car driving at highway speed, and then multiply that speed by 20. That's how fast the winds can be. So how is that even possible? If Neptune is so far from the Sun, where does the energy come from? That's the interesting part. Neptune actually produces more internal heat than it receives from the Sun. This heat rises from deep inside the planet, and as it moves outward, it creates motion in the atmosphere. This motion turns into powerful winds, so instead of being driven mainly by sunlight, Neptune's weather is powered from within. Now imagine standing in such a place. Of course, you couldn't actually stand there. Neptune is a gas giant, like Jupiter. There is no solid surface to stand on. But imagine being in its atmosphere, surrounded by clouds, floating within layers of gas. At first, everything might seem calm from a distance. Soft blue colors, smooth patterns. But within those clouds, the winds are moving at incredible speeds. Now here's a question. Would you feel those winds the same way you feel wind on Earth? Not exactly. Neptune's atmosphere is very different. It's made mostly of hydrogen, helium, and methane, and the density changes depending on how deep you go, so the experience would not be like standing in a storm on Earth. But the force of the movement would still be there, pushing, pulling, shaping the entire atmosphere. Now think about what happens when wind moves that fast. On Earth, strong winds can knock things over, lift objects, cause damage. But on Neptune, the scale is much larger. These winds shape entire weather systems. They create massive storms, dark spots in the atmosphere that can grow and fade over time. One of these storms, known as the Great Dark Spot, was once observed to be large enough to fit Earth inside it. Imagine a storm that could swallow an entire planet. That's the scale of Neptune's weather. Now think about temperature. Neptune is extremely cold. Temperatures in the upper atmosphere can drop to around -200 degrees Celsius. That's colder than anything we naturally experience on Earth, colder than the coldest winter imaginable. So you have this combination, extreme cold and extremely fast winds. Together, they create an environment that feels both still and active at the same time. Now here's something interesting. Even though the winds are incredibly fast, the atmosphere itself can appear smooth from far away. The clouds form patterns, bands, swirls, but they move in ways that are not immediately obvious unless you observe them over time. It's like watching a slow-moving river from a distance. At first, it looks calm, but if you watch closely, you see the movement, the flow. Now imagine that flow happening at incredible speed, but across a vast distance. That's what Neptune is like. So what would happen if something were caught in those winds? It would be carried along, quickly, with little resistance, because there is no solid ground to stop it. No surface to hold onto, just layers of atmosphere, moving continuously. And as you go deeper, pressure increases, temperature changes, the environment becomes even more extreme. So the winds are just one part of a larger system, a system driven by heat, pressure, and motion. Now think about sound. On Earth, wind makes noise. You hear it as it passes by, through trees, around buildings. But in Neptune's atmosphere, the sound would be very different. It might exist in some form, but it wouldn't be something we recognize easily, because the medium, the gas itself, is different, and the scale is so large. So once again, we see a familiar pattern, extreme conditions, but not always in ways we expect. Now imagine observing Neptune from space, a distant blue planet, calm in appearance, almost peaceful. But beneath that appearance, there is constant motion, winds racing across the planet, storms forming and fading, energy moving from the inside outward. It's a reminder that distance can hide intensity. What looks smooth and quiet from far away can be incredibly active up close. So if you were near Neptune, watching its clouds, everything might seem slow, gentle, but in reality, those clouds would be moving faster than anything we experience in daily life. Faster than the fastest winds on Earth, faster than storms we can imagine. And yet, it all happens without any dramatic signal. No loud warning, no sudden change, just continuous motion, endless, driven by forces deep within the planet. And once again, space shows us something interesting. Danger doesn't always come from sharp edges or sudden events. Sometimes it comes from scale, from speed, from forces that are always present, always moving. And Neptune's winds are a perfect example of that. A world where the air itself moves faster than anything we know, quietly, constantly, across a planet that seems calm, until you look a little closer. There are places in the universe where gravity becomes something very different, not just a gentle pull that keeps your feet on the ground, not even a strong force like on a massive planet, but something far more extreme, so extreme that it changes the shape of things, even the shape of you. These places are called black holes. You may have heard of them before, objects so dense that their gravity is incredibly strong enough that even light cannot escape once it gets too close. That's why they appear black, not because they are empty, but because nothing can leave them. Now imagine approaching one. From a distance, it might not look like much. You wouldn't see a solid surface, no clear shape like a planet. Instead, you might see a dark region surrounded by a glowing ring of light. That light comes from material, falling in, heating up as it moves faster and faster. But as you get closer, something strange begins to happen. Gravity is no longer the same across your body. Here on Earth, gravity pulls on you evenly. Your head and your feet feel almost the same pull. The difference is so small you never notice it. But near a black hole, that difference becomes very large. Your feet, being closer to the black hole, would feel a much stronger pull than your head. This creates a stretching effect. It's called tidal force, and it's one of the most unusual effects of extreme gravity. So what does that actually mean? Imagine holding a piece of soft dough. If you pull gently on both ends, it stretches, becomes longer and thinner. Now imagine that same effect happening to your body. Your feet are pulled more strongly than your head, so your body begins to stretch. At the same time, the sides of your body are pulled inward, making you thinner, so you are stretched and squeezed at the same time. This process is sometimes called spaghettification, because objects become long and thin, like strands of spaghetti. It sounds dramatic, but it's a natural result of how gravity behaves near a black hole. Now here's a question. Does this happen instantly? It depends on the size of the black hole. For smaller black holes, the change in gravity from one point to another is very sharp, so the stretching effect happens quickly. For larger black holes, the change is more gradual, so you might not notice it right away. At first, things could feel almost normal, but as you move closer, the effect increases, slowly becoming stronger, until it becomes impossible to resist. Now think about what makes black holes so powerful. It's not just their mass, but how concentrated that mass is. Imagine taking something as massive as a star and compressing it into a much smaller space. It's like taking a mountain and shrinking it down to the size of a grain of sand. All that mass, packed tightly together. That's what creates such strong gravity. Now consider this. If you were far enough away, you could orbit a black hole, just like you orbit a planet. Gravity would still pull on you, but not in an extreme way. It's only when you get closer that things change, and there is a boundary around a black hole called the event horizon. Once you cross it, there is no way back, not because something stops you, but because the pull becomes too strong to escape. Even light, which moves faster than anything we experience, cannot get out. So what would it feel like approaching that boundary? From the outside, someone watching you would see something unusual. You would appear to slow down, as if time itself is stretching, but from your own perspective, time would feel normal. You would continue moving forward, unaware of how things look from the outside. This difference in how time is experienced is another effect of strong gravity. Now think about the stretching again. As you move closer, the difference in gravity between your head and your feet increases. At first it might feel like a slight pull, then stronger, then much stronger, until the forces become overwhelming, and this happens without sound, without warning, just a gradual increase in force. Now imagine floating near a black hole. The space around you would be distorted, light bending in unusual ways, stars appearing stretched or shifted. It wouldn't look like the sky we see on Earth. Everything would feel different, because gravity is affecting not just objects, but space itself. That's one of the most fascinating parts. Black holes don't just pull on things, they change the structure of space around them, bending it, shaping it. So if you were near one, you wouldn't just feel the pull, you would see its effects everywhere. Now here's something interesting. Black holes are not rare. They exist throughout the universe. Some are small, some are extremely large. At the center of many galaxies, including our own, there is a supermassive black hole, one with a mass millions or even billions of times greater than our Sun. But because of the vast distances between objects in space, they don't usually affect us directly. They remain far away, quiet, distant. So why do they matter? Because they show us how extreme gravity can become, how the same force that keeps your feet on the ground can, under different conditions, stretch and reshape matter itself. So if you were near a black hole, everything might feel calm at first. No sound, no sudden movement, just a steady pull. But as you move closer, that pull becomes something else, stronger, uneven, changing the shape of everything it touches. And once again, we see the same pattern. The universe doesn't always show its danger clearly. Sometimes, it reveals it slowly through forces that increase over time, until they become impossible to escape. And black holes are a perfect example of that. A place where gravity itself becomes the danger, stretching, quietly reshaping everything that comes too close. There are objects in the universe that take everything we understand and push it to the edge. Neutron stars are one of them. They are what remain after a massive star reaches the end of its life and collapses. But instead of forming a black hole, the collapse stops at an incredibly dense state. What's left behind is something small, but extremely heavy. To understand how unusual this is, imagine taking a star much larger than our Sun and compressing it down to the size of a city, not a country, not a continent, just a city, something you could drive across in less than an hour. And yet, all that mass is still there, packed into that small space. So what does that mean? It means the density is incredibly high. If you could take just a teaspoon of material from a neutron star, it would weigh billions of tons. That's like taking a small spoonful and having it weigh more than a mountain, more than all the buildings in a large city combined. It's difficult to imagine something so small being so heavy. But that's what happens when matter is compressed to this level. Now here's a question. What is that material made of? Inside a neutron star, things are very different from what we experience on Earth. Atoms, which normally have space between their parts, are squeezed so tightly that they break down. Electrons and protons combine to form neutrons, and these neutrons are packed closely together. So instead of normal matter, you have something much denser, a kind of matter that doesn't exist naturally anywhere else. Now think about gravity. Because the mass is so concentrated, the gravity at the surface of a neutron star is extremely strong, much stronger than on Earth. If you were somehow able to stand on its surface, the pull would be overwhelming. It would be like having the weight of billions of people pressing down on you at once, impossible to withstand. Now imagine dropping something onto a neutron star, even a small object. As it falls, it would accelerate very quickly because of the strong gravity. By the time it reaches the surface, it would be moving at a huge speed. When it hits, the impact would release a large amount of energy. Even something small could create a powerful effect. Now, here's something interesting. Neutron stars are not only dense, they also spin very fast. Some of them rotate many times per second. Imagine something the size of a city spinning faster than a kitchen blender. That's the scale we're talking about. This rapid rotation can create beams of radiation that sweep through space. When these beams pass by Earth, we detect them as regular pulses. That's why some neutron stars are called pulsars. They act like cosmic lighthouses, sending out signals at precise intervals. Now think about the surface. Unlike gas giants, neutron stars have a solid outer layer, but it's not like rock or metal. It's something much stronger. The material is so dense and tightly packed that it forms a crust unlike anything on Earth. If you could imagine the strongest material you know, and then make it even stronger, that might give you a sense of it. Now here's a question. Would it be possible to walk on that surface? In theory, it's solid. But in practice, the gravity would make it impossible. You wouldn't be able to stand, move, or even exist in that environment. The forces involved are far beyond what the human body can handle. Now think about time. Just like near black holes, strong gravity can affect time. On a neutron star, time would pass slightly slower compared to far away. It's not something you would notice directly, but it's measurable. Another example of how extreme environments change the rules we are used to. Now imagine being near a neutron star. From a distance, it might appear small, bright, sometimes flashing as it rotates. But as you get closer, the intensity becomes clear. The gravity, the radiation, the speed, all working together. Now here's something else to consider. Magnetic fields. Some neutron stars have incredibly strong magnetic fields, much stronger than anything we experience on Earth. So strong that they can affect atoms themselves. We'll explore that more later, but it shows how extreme these objects can be. Now think about how neutron stars form. A massive star lives its life, producing energy through fusion. But eventually, it runs out of fuel. When that happens, it can no longer support itself against gravity, so it collapses, and in that collapse, everything is compressed. The result is a neutron star, small, dense, and incredibly powerful. So what makes neutron stars dangerous? It's not just one thing. It's everything combined. Extreme density, strong gravity, fast rotation, intense radiation, each one pushing the limits of what matter can do. And together, they create an environment that is far beyond anything we experience on Earth. Now imagine observing one from a safe distance, point of light in the darkness, pulsing steadily, almost like a heartbeat, calm in appearance, but behind that calm, there is immense energy, forces that reshape matter itself. So if you were near a neutron star, everything might seem quiet at first, still, controlled. But the closer you get, the more those hidden forces reveal themselves, not suddenly, but steadily, until it becomes clear that this is not just another object in space. It's something entirely different, a place where matter is pushed to its limits, where gravity and density reach levels that are hard to imagine. And once again, the universe shows us something unexpected. Danger doesn't always come from size alone. Sometimes it comes from how much is packed into a small space. And neutron stars are a perfect example of that. small in size, but holding forces so great that even a tiny piece would outweigh anything we know. Quiet, distant, but carrying the weight of something far beyond everyday experience. There is a force you experience every day, even if you don't notice it. Magnetism. It's what makes a compass point north, what holds a magnet to a refrigerator, what quietly shapes part of the world around you. On Earth, magnetic fields are gentle, useful, predictable, but in space, there are places where magnetism becomes something much more extreme. Magneteers are one of those places. They are a special type of neutron star, small, dense, but with a magnetic field so strong that it's hard to imagine. To understand how strong, let's start with something familiar. A typical refrigerator magnet is a magnetic field that can hold a piece of paper in place. Earth itself has a magnetic field which protects us from radiation and helps guide compasses. Now imagine something far stronger. A magnetar's magnetic field is trillions of times stronger than Earth's. Not a little stronger, not even thousands of times stronger, trillions. That's a number so large, it's difficult to picture. If Earth's magnetic field is like a gentle breeze, a magnetar's field is more like a force that reshapes everything around it. So what does that actually do? Magnetic fields affect charged particles. They guide their motion, but at the strength of a magnetar, the effect goes much deeper. It can influence atoms themselves. Imagine taking an atom, something incredibly small, and stretching it, changing its shape. That's the kind of effect we're talking about. The magnetic field becomes strong enough to distort the structure of matter. Now here's a question. How far does that effect reach? Even from thousands of kilometers away, a magnetar's field could still have noticeable effects. If you were somehow close enough, it could interfere with electronic systems, disrupt signals, and at closer distances, the effects would become more intense. Now imagine holding something made of metal near such a field. On Earth, a magnet pulls gently, but near a magnetar, the force would be overwhelming. Not just pulling, but potentially tearing things apart at a microscopic level. Because the field is not just strong, it's extremely concentrated. Now think about what would happen to the human body. The body relies on electrical signals. Your brain sends signals through your nerves. Your heart beats through electrical activity. All of this depends on delicate balances. A magnetar's field could disrupt those processes. Not in a dramatic, visible way, but by interfering with the signals that keep the body functioning. Now here's something interesting. Magnetars don't just have strong magnetic fields. They also release energy in sudden bursts. These are called starquakes. The crust of the neutron star shifts slightly, releasing energy. And when that happens, it can send out a burst of radiation, a powerful wave moving through space. These bursts can be detected from very far away, even across the galaxy. That gives you a sense of their strength. Something happening on a small object, sending signals across vast distances. Now imagine observing a magnetar from afar. It might appear as a small point of light, sometimes steady, sometimes flashing, but hidden within that light is an intense magnetic field, constantly present, always affecting its surroundings. Now think about scale again. Neutron stars are already incredibly dense. Magnetars take that and add another layer. Extreme magnetism, so you have gravity pulling strongly, and magnetism shaping matter at the same time. Two powerful forces working together. Now here's a question. Why do magnetars have such strong magnetic fields? The exact reason is still being studied, but it likely comes from the way the star collapses and rotates. As the star shrinks, its magnetic field becomes more concentrated, like taking a wide field and compressing it into a smaller space. The strength increases dramatically. It's similar to how spinning faster can increase energy. The smaller and denser the object becomes, the more intense its properties can be. Now think about how rare these objects are. Not every neutron star becomes a magnetar. They are a special case, an extreme version of something already extreme, so encountering one up close would be very unlikely. But the fact that they exist tells us something important. The universe can produce conditions far beyond what we experience on Earth. Forces that go beyond everyday understanding. Now imagine being near a magnetar. From a distance, everything might look calm, just a small, distant object. But as you move closer, the effects would become noticeable, not through sound, not through visible motion, but through changes in how matter behaves, in how energy moves, in how systems respond. Because the magnetic field would be everywhere around you, invisible, silent, but incredibly strong. Now think about how we usually think of danger. Something loud, something sudden, something we can see. Magnetars don't behave that way. Their danger is quiet, constant, always present. A force that doesn't need to move or change to be powerful. And once again, we see the same pattern. Space is full of extremes, but those extremes are often hidden, not obvious at first glance, revealed only when you look closer or get too near. So if you were observing a magnetar from afar, it might seem like just another star, a point of light in the distance, but behind that light is something far more intense, a magnetic field so strong that it changes the nature of matter itself, quietly, constantly, without any visible warning. And that's what makes magnetars so fascinating. They take a familiar idea, magnetism, and stretch it to a level that feels almost unreal, showing us that even the forces we think we understand can become something entirely different in the right conditions. And in space, those conditions exist, far away, but always waiting to be discovered. Stars feel permanent. When you look at the night sky, they seem steady and unchanging. The same patterns appear again and again, night after night, year after year. It's easy to think of them as constant, something that simply exists, without beginning or end. But stars, like everything else, have lifetimes. They are born, they live for millions or billions of years, and eventually, they die. And when some stars die, they don't fade quietly. They end in one of the most powerful events in the universe, a supernova. At first, it might not sound dramatic, a star reaching the end of its life. But what actually happens is far from gentle. To understand it, imagine something familiar. Think of a fire that slowly burns through its fuel. At first it burns steadily, but as the fuel runs out, the fire changes. It flickers, it becomes unstable, and eventually it goes out. Now take that idea and scale it up to something millions of times larger. A star spends most of its life fusing elements in its core, turning hydrogen into helium, releasing energy in the process. That energy pushes outward, balancing the force of gravity pulling inward. As long as that balance exists, the star remains stable. But over time, the fuel begins to run out. The balance starts to shift. Gravity begins to win. The core collapses inward, and when that happens, everything changes very quickly. In a fraction of a second, the core compresses, then rebounds. And that rebound sends a shockwave outward through the star. The outer layers are blown away in a massive explosion. That explosion is a supernova. So how powerful is it? In just a few seconds, a supernova can release more energy than the sun will produce in its entire lifetime. Think about that. Billions of years of energy, released almost instantly. It's like taking the total energy of the sun over its entire existence and compressing it into a moment. Now imagine what that would look like. From a distance, a star suddenly becomes much brighter, sometimes outshining entire galaxies for a short time. A point of light in the sky, becoming one of the brightest objects in the universe, and then, over time, it fades. But the explosion itself continues to expand, sending material outward in all directions. Now here's a question. What happens to all that material? It spreads out into space. Gas, dust, elements created during the life of the star and during the explosion itself. These materials can travel across vast distances, eventually becoming part of new stars, new planets, even new systems. In a way, supernovae are part of a cycle. They end one star's life, but help create the building blocks for new ones. Now think about distance. If a supernova happened close to Earth, it could have serious effects. Radiation, energy, changes to the surrounding space. But fortunately, stars are very far apart. The nearest stars are so distant that even light takes years to travel between them. So when supernovae happen, they are usually far enough away that we only see the light, a bright flash in the sky, a distant event. Now imagine being closer, not too close, but close enough to see the explosion clearly. The brightness would increase rapidly. The star would seem to grow in intensity, and then the outer layers would begin to expand, moving outward at incredible speeds, thousands of kilometers per second, fast enough to travel across Earth in just a few seconds. Now think about the shock wave. As it moves through space, it carries energy and material. It interacts with surrounding gas and dust, creating patterns, shapes, expanding clouds that can be seen long after the explosion. Some of these remnants are beautiful, colorful, complex, but behind that beauty is an incredibly powerful event. Now here's something interesting. Not all stars end this way. Smaller stars like our Sun have a quieter ending. They expand into red giants and then shed their outer layers more gently. But larger stars, much larger than the Sun, are the ones that produce supernovae. Their size and mass create the conditions for such powerful endings. Now think about time again. A star can live for millions or billions of years, but its final moments happen very quickly. It's like a long story that builds slowly and then ends in a sudden, powerful conclusion. So if you were observing a supernova, everything might seem normal at first. A steady star, quiet, unchanging, and then, suddenly, it brightens, expands, releases energy on a scale that's hard to imagine, all within a short time. And then, slowly, it fades again, leaving behind a cloud of material, a reminder of what once was. Now think about what remains after the explosion. Sometimes, a neutron star is left behind. Sometimes, a black hole. The core that collapsed becomes something new, something even more extreme. So a supernova is not just an ending. It's also a transformation, from one state to another. Now imagine the universe as a whole, stars forming, living, dying, over and over again. Each supernova adding material back into space, helping create new stars, new planets, new possibilities. And once again, we see a pattern. The universe is not static. It is always changing, always moving, even in ways we cannot see directly. So if you are watching the night sky, everything might seem calm, peaceful, unchanging, but somewhere far away, a star could be reaching the end of its life, preparing for a moment of incredible energy. A brief, powerful event that outshines almost everything around it, and then fades, quietly, leaving behind the pieces for something new. Because in space, Even the most violent events are part of a larger cycle, a balance between creation and destruction, where endings are not just endings, but the beginning of something else. When you look at a galaxy, it feels still, a soft spiral of light. Billions of stars arranged in patterns that seem calm and balanced. From a distance, it looks like a photograph that never changes. But galaxies are not frozen, they are moving, slowly but constantly, and sometimes they move toward each other. When that happens, something incredible takes place. Galaxies collide. At first, that might sound like a sudden crash, like two objects smashing together in a moment, but that's not how it happens. Because galaxies are enormous, the distance between stars inside a galaxy is very large, so when two galaxies meet, they don't collide in the way solid objects do. Instead, they begin to pass through each other, slowly, over millions of years. Imagine two clouds drifting into one another. They don't shatter, they blend, they stretch, they reshape. That's closer to what a galaxy collision is like. Now here's a question. If galaxies pass through each other, do stars crash into one another? Surprisingly, almost never. Even though a galaxy contains billions of stars, the space between them is so vast that direct collisions are very unlikely. To picture this, imagine two groups of tiny beads spread out across a huge field. If you throw the groups toward each other, most beads would pass by without touching. That's how much empty space there is. So if stars don't usually collide, what actually happens? Gravity. That's the key. As galaxies move closer, their gravity begins to interact, pulling on stars, changing their paths, stretching the shape of the galaxies. Arms of stars can be pulled outward, forming long streams. The structure begins to change. It's like taking a smooth shape and slowly stretching it into something new. Now imagine watching this from far away. At first, two galaxies approach each other, their shapes still clear. Then, as they get closer, their edges begin to distort. Arms twist, stars shift. Over time, the two galaxies become one. A new shape forms, different from either of the originals. Now think about time. This process doesn't happen quickly. It takes millions, sometimes billions, of years. So from a human perspective, it's almost impossible to see it happen in real time. But when we observe different galaxies at different stages, we can piece together the process, like looking at snapshots of different moments in a very long story. Now here's something interesting. When galaxies collide, new stars can form. As gas clouds within the galaxies interact, they can become compressed. And when that happens, new stars are born. So even though the collision might sound destructive, it also creates new beginnings, new light, new systems. It's a mix of change and creation happening at the same time. Now think about our own galaxy. The Milky Way. It is not isolated. It is part of a group of galaxies. And one of those galaxies, called Andromeda, is moving toward us, very slowly but steadily. So what does that mean? In about 4 billion years, the Milky Way and Andromeda are expected to collide. That might sound alarming at first, but remember what we said earlier. Stars are so far apart that direct collisions are unlikely. So even during this event, the chance of our solar system hitting another star is extremely small. But the night sky would change. Stars would shift positions. New patterns would form. The structure of the galaxy would evolve. Now imagine standing on a planet during such a time. The sky would look different, more crowded, more dynamic. Light stretching across the sky in new shapes. It would be a slow transformation, not something that happens in a single moment, but something that unfolds over millions of years. Now think about the scale again. a single galaxy can contain hundreds of billions of stars. And when two galaxies interact, all of those stars are influenced by gravity, each one following a new path, each one part of a larger motion. It's like watching an enormous dance, where every movement is guided by invisible forces. Now here's a question. If galaxies are constantly moving and interacting, is the universe stable? In a way, yes, but it's also always changing. Structures form, evolve, combine, separate. It's not static. It's a dynamic system, always in motion, even if that motion is slow. Now imagine looking at a galaxy collision from a great distance. Two glowing shapes moving toward each other. At first, they seem separate, then they begin to stretch, their edges blending, arms reaching outward, eventually forming a single, larger galaxy, all happening quietly, without sound, without sudden impact, just slow, steady change. And once again, we see something unexpected, a collision that is not violent in the way we imagine, no loud crash, no instant destruction, instead, a gradual merging, a reshaping of structure over time. So if you were observing this, everything might feel calm, almost peaceful, even though something massive is happening. Because in space, even the largest events can unfold slowly, quietly, without urgency. And that's what makes galaxy collisions so fascinating. They show us that scale changes everything. What would be violent on a small scale becomes gentle on a larger one, not because it's less powerful, but because it happens over such a vast time and distance. And in that slow motion, the universe continues to reshape itself, one galaxy at a time. When you look at the night sky, it feels still. Stars appear fixed. Galaxies seem like distant lights that don't change. It's easy to imagine the universe as something stable, something that has always been the same, but that's not actually what's happening. The universe is expanding, very slowly, but constantly. Everything is moving apart, not just objects drifting through space, but space itself, stretching. That idea can feel a bit strange at first. So what does it really mean? Imagine drawing small dots on the surface of a balloon. Each dot represents a galaxy. Now slowly inflate the balloon. As it expands, the dots move farther apart, not because they are moving across the surface, but because the surface itself is stretching. That's similar to what is happening in the universe. Galaxies are not just traveling through space. Space itself is expanding, carrying them along. Now here's a question. If everything is moving away from everything else, does that mean we are at the center? It might seem that way. But actually, every point in the universe sees the same pattern. No matter where you are, everything appears to be moving away from you. Just like any dot on the balloon would see other dots moving away as it expands. So there is no single center. Expansion happens everywhere at once. Now think about distance. The farther away a galaxy is, the faster it appears to move away. This has been observed through light. When we look at distant galaxies, their light shifts slightly. This shift tells us they are moving away from us. And the farther they are, the greater the shift. It's like watching cars on a road. Nearby cars move slowly relative to you, but cars far down the road appear to move faster. Now imagine that effect on a cosmic scale, galaxies billions of light years away, moving apart at incredible speeds. Now here's something interesting. The expansion of the universe is not slowing down. It's actually speeding up. Something is causing space to stretch faster over time. This effect is often linked to what scientists call dark energy. We don't fully understand it yet, but we know it exists because of how galaxies behave. It's like an invisible force pushing everything apart. Now think about what this means for the future as time goes on. Galaxies will move farther and farther away from each other. Some will become so distant that their light will no longer reach us. They will fade from view, not because they disappear, but because the space between us and them becomes too large. It's like watching a light move farther and farther away until it becomes too faint to see. Now imagine being in the distant future, looking at the sky. There would be fewer galaxies visible, less light from distant places. The universe would feel more isolated, more empty. Now here's a question. Does this expansion affect smaller systems, like our solar system or our galaxy? The answer is no, not directly. Gravity holds these systems together, so even though the universe is expanding, local structures remain stable. Planets stay in orbit. Stars remain in galaxies. But on very large scales, beyond those gravitational bonds, expansion takes over. Now think about scale again. The distances involved are enormous. Light itself takes years to travel between stars, millions of years between galaxies. So the expansion of the universe happens over distances that are hard to imagine. It's not something you can feel, not something you can see in a single moment, but over long periods, the change becomes clear. Now imagine space itself as something flexible, not rigid, not fixed, but able to stretch, like fabric being pulled slowly outward. Everything within it moves as the fabric expands, and that includes galaxies, clusters, and larger structures. Now think about what that means. The universe is not just a place where things happen. It is something that changes, something that evolves over time. And that change is not driven by any visible force. No wind, no pressure you can feel. Just a quiet expansion happening everywhere at once. Now imagine observing this from far away. You see galaxies drifting apart, slowly, steadily. No sound, no sudden motion, just gradual separation, over millions and billions of years. Now here's something to consider. If the universe continues to expand, what happens to connection? Over time, regions of space become more isolated. Galaxies move beyond each other's reach. Light takes longer to travel. Eventually, some parts of the universe may become completely unreachable from others. Not because something blocks the path, but because the distance grows too quickly. Now think about how quiet this process is. There is no signal, no visible line showing space stretching, no moment where you can point and say, "It changed right there." It's continuous, subtle, always happening, and that makes it easy to overlook, because it doesn't feel like motion in the way we are used to. It's not something moving through space, it's space itself changing. Now imagine floating in the universe, looking out in every direction. Everything seems still, calm, but over time, the distances between objects are increasing, slowly separating everything, and that separation continues endlessly. And once again, we see a familiar idea. The universe doesn't need to act suddenly to be powerful. It can change slowly, quietly, over immense timescales, and those changes can shape everything. So if you were watching the universe over billions of years, you would see it stretching, expanding, carrying galaxies farther apart, not with force you can feel, but with a steady motion that never stops. And that's what makes this idea so fascinating. The universe itself is not fixed. It is moving, growing, changing, even when everything appears completely still. When we think about danger, we often imagine something active, something that moves toward us, something that tries to harm. A storm, a predator, an impact. But space is different. Its danger is not active. It doesn't chase, it doesn't react, it doesn't even notice. And that is what makes it so unusual. Because the ultimate danger of space is not that it is hostile, but that it is indifferent. It does not provide what you need to survive. It does not adjust for your presence. It simply exists as it is, and everything we've explored leads back to this idea. The vacuum that offers no air, the lack of pressure that the body depends on, radiation moving silently through space, extreme temperatures shifting between heat and cold, tiny particles moving at incredible speeds, worlds that look calm but cannot support life. Each of these is not an attack, not an event directed at you. They are just conditions, always there, unchanging in their nature. Now think about Earth. It feels safe because it supports life. Air to breathe, water to drink, temperature that stays within a narrow range, gravity that holds everything together. But even Earth is not actively protecting you. It simply has the right conditions that allow life to exist. Space, on the other hand, does not have those conditions, so survival becomes something you have to create. With technology, with planning, with constant awareness. Now here's a question. Why does space feel so calm if it is so dangerous? Because nothing in space signals danger in the way we expect. There is no sound to warn you, no wind to feel, no movement you can sense directly. It is quiet, still, and that stillness can feel peaceful. But that peace is not safety. It's simply the absence of interaction. Now imagine drifting in space. No sound, no resistance, just a slow, gentle motion. Stars around you, darkness stretching in every direction. It might feel like the most peaceful place you've ever been, and yet, without protection, it is one of the most dangerous environments imaginable. Not because something is happening to you, but because nothing is supporting you. Now think about how everything we've discussed connects. The lack of oxygen takes effect in seconds. Pressure differences affect the body quickly. Radiation works slowly, but constantly. Temperature changes exist, but don't always act immediately. Gravity can stretch or compress depending on where you are. Each of these is a piece of the same idea. Space does not adapt to you. You must adapt to it. Now consider this. On Earth, if something changes, you can often respond. Move to a different place, find shelter, adjust your environment. But in space, options are limited. You rely on what you bring with you, your spacecraft, your suit, your systems, each one carefully designed to replace what space does not provide. Air, warmth, protection. Without those, survival is not possible, and that leads to something interesting. Space exploration is not about conquering space. It's about learning how to exist within it, how to create small environments where life can continue, even in a place that does not support it naturally. Now imagine a spacecraft floating quietly. Inside, everything is controlled. Air flows, temperature stays stable. Systems work together to create a small, safe environment. But just outside that thin boundary, everything changes. No air, no warmth, no protection, just the conditions we've been talking about. So the difference between safety and danger can be very small. Just a layer of material, a thin wall, a suit, and that contrast is constant, always present. Now think about distance. Space is vast, so vast that even light takes years to travel between stars. And in that vastness, there is no central place, no single point of focus, just endless space in every direction. That scale adds to the sense of indifference, because in such a large universe, individual events are small, quiet, unnoticed. Now here's another question. Does space care if something survives or not? No, it doesn't respond. It doesn't change based on presence. It remains the same. And that's what makes it different from the environments we are used to. On Earth, life and environment are connected. They interact, They influence each other. In space, that connection is not there. Now imagine looking at the universe as a whole, galaxies moving apart, stars forming and fading, planets existing in different conditions, all of it happening without intention, without awareness, just following the laws of physics. And within that system, life exists in small pockets, places where conditions happen to be right. Now think about how rare that is, how specific the conditions need to be. Air, water, temperature, protection, all balanced together. That balance exists on Earth, but not in most of space, so survival beyond Earth becomes something we must build. Carefully, deliberately, one system at a time. Now imagine, again drifting in space. Everything feels calm, still, almost timeless, but that calm hides something deeper. A complete absence of support. No help, no resistance, no adjustment. Just a place where everything continues as it always has. And if you are not prepared, that environment takes effect immediately. Not because it acts, but because it does not act at all. And that is the final idea. Space is not dangerous in the way we usually think. It does not need to be, because it offers nothing. And in that absence, everything becomes your responsibility. Every breath, every movement, every moment of survival. And once you understand that, the quiet of space feels different, still, peaceful, still beautiful, but also something else. A reminder that beyond Earth, life is not supported. It is sustained, carefully, within small spaces of safety, surrounded by a universe that simply continues, unaware, unchanged, and endlessly vast.